and welcome to this session on novel functionalities in nano to mesoscale magnetism. My name is Naomi Leo. I'm a postdoc at the CIC Nanogune in Spain, and I'm the host of this session. And at this point, I want to thank the organizers who managed the feed to change within a very short amount of time to go from a complete on-site conference to an online event, which is free of charge to attend. And I think they really, really worked hard to provide us with the opportunity to kind of meet up in a way this year where so many possibilities to meet colleagues are so limited. And we will now start with the session. Just a few reminders of the rules. I would like to ask the speakers to stick to their time. I have a very good timing device with me, and I will try my best to interrupt you or tell you when you're going over time. And for the audience, please mute your microphone and your video. And if you have questions, please write them in the chat so we can either read the questions directly from the chat, or if they are a bit more complicated, we will also allow you to, or that you can speak them and then the speakers can answer. With this said, I'm happy to introduce the first speaker, Claire Donnelly, who will give a presentation on X-ray imaging of three-dimensional magnetic systems and their dynamics. So Claire, please go ahead.
So, thank you, Naomi. I'll share my screen now. Can you see? Great, okay. So I'll just start by thanking Naomi for the opportunity for the introduction and the opportunity to speak to you all this morning. And again, add my thanks to you and the organisers for creating this online conference. It's a really great way to see and hear from everybody in these really unusual times. So so my name is Claire Donnelly, and I'm going to speak to you today about our work on X-ray imaging of 3D magnetic systems. And just a quick mention about my affiliations at the top of the slide. I'm currently a postdoc at the University of Cambridge, but part of the work that I'm going to show to you today has been done during my PhD and postdoc at the Paul Scherrer Institute and the ETH Zurich, hence the three affiliations in this slide. So to get started, about 3D magnetism, why is this such an exciting and rich topic? Well, as I'm sure you're all very aware, nanomagnetism has been of great interest in the last few decades, in fact. There's been a huge amount of work and progress done both for fundamental physics and device applications. However, until very recently, the vast majority of work has actually been, has involved two-dimensional magnetic systems and planar arrays, due in fact to the fact that these are already very interesting systems, but also there are certain limitations when it comes to their fabrication. When we consider going to the next dimension, so going to 3D, there are a number of opportunities for advances. So you can see already from the schematic that there are a huge number of new shapes that we can imagine having. But as well as the new geometries, there are also new physics and new opportunities for devices to be had. And I'll start with an example of possibly the most well-known 3D nanomagnetic device, which is that of the racetrack memory, proposed by Stuart Parkin in 2008, who will speak actually later in this session. The racetrack proposes essentially a 3D architecture that allows for very high density magnetic data storage. But in addition to the 3D architectures allowing for, let's say, high density and properties along those lines, three-dimensionality can actually change the magnetic properties and the physics of our systems. And we can take a look at the most let's say, basic unit cell, so to speak, of 3D magnetism, which is that of a cylindrical or a nanowire or a magnetic nanochip, in which theoretical works in the recent years have predicted very exotic domain wall dynamics, including magnetochirality effects, as well as the spin Cherenkov effect, for example. And with the first experimental demonstration of domain wall dynamics in cylindrical nanowires by the group of Olivier Fruchart in France, there's actually been a very nice demonstration of very high domain wall velocities, consistent with what was predicted, and this is due to the topological stability of the domain walls in these systems. Now, in addition to nanowires, we also their three-dimensionality also provides advances or opportunities in a number of other fields. For example, in the case of frustrated magnetic systems and artificial spin ice, if we take the generally planar arrays of nanomagnets and we lift them up into 3 dimensions, there's a possibility for very complex energy landscapes, extensive degeneracy, and a true Coulomb phase. When it comes to another very well-known and very exciting topic of magnetism, which is topological structures, such as skyrmions, when we go to 3-dimensional extended or even bulk-like systems, we have the possibility of observing like skyrmion tube structures and even buried topological transformations that can include the presence of magnetization singularities. Finally, one of the holy grails of 3D nanomagnetism at the moment is that of the magnetic Hopfion. So as skyrmions are a 2-dimensional topologically protected object, so Hopfions are their 3D equivalent. And there's been a number of papers in recent years, in the last couple of years actually, predicting the existence of these magnetic Hopfions, but they've still not been seen experimentally. So as you can see, there's a huge amount of very interesting prospects of 3D nanomagnetism. But in order to actually take advantage of these and actually visit, or let's say, look at them experimentally, we need new experimental methods. And there's a couple of main sort of, let's say, avenues in which we need progress. So first of all, in terms of the fabrication, in order to realize these 3D magnetic systems, we need essentially 3D printing techniques for magnetic materials. And there's been a couple of ways in which this has been achieved in recent years. First of all, with the fabrication of non-magnetic scaffolds with, for example, 2-photon lithography, there's been the realization of 3D artificial spin ice systems, as well as a buckyball structure. And in addition, there's also the possibility of direct writing of the magnetic materials, creating nanowire arrays, as you can see in this SEM image here. And more recently, my current group has developed a new capability to realize arbitrary 3D geometries at the nanoscale. So as you can see, there's a huge number of possibilities at our fingertips now. So now that we have access to these 3D magnetic nanostructures, the next challenge is actually visualizing them and understanding what's going on, i.e. we need 3D characterization techniques. Now, when we consider that, we need essentially 3D magnetic imaging or magnetic tomography. And in recent years, there's been a number of developments in this, where it's been achieved with electron magnetic tomography, where you can look at relatively thin samples, so a couple of 100 nanometers in thickness, but with high spatial resolutions. With neutrons, where you can look at much thicker samples, so up to millimeters in size, but with lower spatial resolutions, so on the order of tens to hundreds of micrometers. And lastly, with X-rays, where we can somehow bridge the gap between these two regimes. We're able, using hard X-rays, to look at larger micrometer-sized materials whilst retaining these high spatial resolutions of down to nanometer scale that we can achieve with electrons. And in this talk today, as you can maybe guess from my title, I'm going to focus on the 3D characterization of these magnetic systems, specifically that with X-rays. So to start with, let's have a think about what X-ray magnetic tomography really means and what we actually needed to develop in order to achieve this. And I'll start with introducing the concept of tomography that I'm sure you're all very familiar with, but we can just have a quick recap. So in tomography, the idea is, as shown in this schematic, that you have your 3-dimensional sample and you measure a number of different transmission projections, 2-dimensional projections for many different sample orientations with respect to the X-ray beam. Now that you have this selection of projections, you use a reconstruction algorithm to reconstruct the internal 3D structure and therefore looking non-destructively within your sample. Now, when we want to extend tomography to magnetic tomography, there were 3, let's say, main challenges facing us back back, when we were developing the technique. The first one was the ability to image projections of the magnetization. Now, as I mentioned, we were using hard X-rays. And hard X-rays, although they allow us to look at much bulkier systems, they have the disadvantage that they have very weak magnetic signals. We managed to overcome these weak magnetic signals by using coherent diffractive imaging techniques, which allow access to the full complex transmission function of your sample with high sensitivity, which allowed us to probe the XMCD signal within our systems and image the magnetization projection with nanometer spatial resolution. So now that we have the basic ingredient for tomography, which is the imaging of the projections, the next question is, what combination of projections did we need? And it soon became clear that a single rotation axis was not going to be sufficient for the probing of a three-dimensional vector field. With one rotation axis, they actually only probe two components of the magnetization. So we implemented a dual axis tomography setup at the CSAX beamline at the Swiss light source in order to probe all three components of the magnetization. So now that we have our, let's say, experimental pieces of the puzzle, the imaging of the projections, and we could measure the projections that we needed in order to probe the magnetization, we needed one last piece of the puzzle, which was combining all of these to obtain the vector field. For this, we developed a new reconstruction algorithm in which we can take all of our XMCD projections measured at many, many different sample orientations and obtain a 3D map of our magnetization vector field. So now that we had all of the, let's see, I've said this so many times, pieces of the puzzle, now we can go on to the next stage, which is the first demonstration of hard X-ray magnetic tomography. And I'll introduce you to the sample that we looked at first, which was a gadolinium cobalt pillar cut from a nugget with a focused ion beam, and it's 5 micrometers in diameter. So what I want to mention here or take a note of is that the internal magnetic configuration of this sample was at that time not known. We thought that it would be relatively smoothly varying magnetic configuration due to the material properties, but there was no way to actually look inside. So what we did first of all was we performed 2D imaging of the structure, which you can see with a single circular polarization at the top. The contrast is very much dominated by the electronic contrast because the magnetic contrast is so weak. But when we take the difference between two circular polarizations, as we see below, we can isolate the contribution of the magnetic component parallel to the X-ray beam. So we see the bright and dark regions corresponding to the magnetization pointing to and away from the X-rays. And so this is great. It tells us immediately that we have a sample that is magnetic, which was a huge relief. But of course, from this single projection, we cannot understand what's going on inside. In order to do that, we performed magnetic tomography, which involved measuring 1,000 of such projections at many different sample orientations. And we used our reconstruction algorithm to reconstruct the internal configuration with 100 nanometers spatial resolution. And as you can see in the video here, and I want to emphasize that this is a static image, but we're just showing it dynamically going through the structure. The magnetization is relatively smoothly varying, but there are a number of twists and turns in the magnetization that are relatively interesting. So in order to take a closer look at what's going on inside the sample, we can first of all consider a horizontal slice indicated by this box here. When we look at the magnetization in this horizontal slice, and we plot the in-plane components with streamlines and the out-of-plane components are represented by the color of the streamlines, we see a relatively interesting configuration that looks relatively familiar. That's because it's composed of a number of topological features. We can identify vortices of the magnetization, where the magnetization curls around a central core, and in the core the magnetization can point up or down. And we also observe their topological opposite, which are anti-vortices, which exhibit a more saddle-like structure, and again have this central core that that can point up or down, so in or out of the plane. So that is a very two-dimensional way to look at our data. However, we have a 3D data set, and in order to really look at this and make the most of this, we wanted to look at a 3D, let's say, volume, specifically the sub-volume. So this is a subset of the data set, surrounding the central vortex that we saw in the previous slide. Now we can look at this in a little bit more detail, and we notice a few things. First of all, on the left-hand side, or considering the out-of-plane component of the magnetisation, on the left-hand side, the magnetisation is pointing relatively up, and on the right-hand side, it's pointing down. And in between these two, let's say, domains, we have this white surface, which corresponds to a magnetic domain wall. Now, what is particularly interesting here is that the core of the vortex, which is represented by this isosurface, actually crosses the domain wall at two different points within this subvolume. And when it crosses the domain wall, the polarization of the vortex actually reverses, as we can see, moving from orange to purple. Now, what this means is actually that the topology of the vortex is changing, and therefore we would expect at these points to find magnetisation singularities, which are known as Bloch points and were first predicted back in the 1960s, but up until this point their 3D structures surrounding them had not yet been observed. So indeed, when we plot the magnetisation in these crossover regions, we observe magnetic structures that actually correspond very well to what is predicted for the structure of Bloch points in the literature. We see at the top what is very consistent with a circulating Bloch point with a vortex in the plane and the magnetisation pointing up and down, above and below. And at the other point, we see a more twisted structure that is consistent with an anti-Bloch point. And since the Bloch, like the vortex and anti-vortex are topological opposites, here we have the Bloch point and anti-Bloch point that we believe may have originated within the bulk as a pair. So this is a really nice demonstration of what is possible when we have these access to these new methods and these new capabilities for imaging 3D dimensional magnetic systems. And it was a really nice first insight into, or not first insight, but an insight into the structure of these Bloch points. However, at this point, we knew that there was still more to be done. And in order to develop the method for 3D imaging further, we identified 3 avenues that we want to pursue. First of all was moving to more flexible experimental geometries in order to be able to look at samples that are not necessarily ideal for tomography. Secondly, we had realized that many of the most exciting properties of 3-dimensional magnetic structures were actually in their dynamics. So the question was, can we go to the 4th dimension? Can we actually image these magnetization dynamics in 3D? And lastly, moving to higher spatial resolutions and therefore being able to look at the magnetization at smaller length scales where things get particularly interesting. So first of all, more flexible experimental geometries. The first question may be, why is this necessary? Why is tomography not a one-size-fits-all? And although tomography is a very effective, non-destructive 3D imaging technique, it is ideal for cylindrical samples. So as you can imagine, when you rotate with a cylindrical sample, the thickness of the sample does not change. However, when we have an alternative geometry of samples, such as a silicon nitride membrane that you can see in the schematic, at certain angles when you rotate the sample, you actually block the X-ray beam, meaning that you have you lose data and you essentially can introduce artifacts into your reconstruction, into the vector field that you obtain from the imaging process. Now, an alternative geometry that allows us to circumvent these limitations is laminography, where instead of in tomography with the rotation axis being perpendicular to the X-ray beam, in laminography we actually tilt it towards the X-ray beam, allowing us to image flat extended samples without these absorption problems. Now, before we could go on to an experimental demonstration of laminography, we first needed to generalize our reconstruction algorithm, because previously we had developed it under the assumption that the data was used for the data consisted of tomographic geometries. We therefore generalized the algorithm by allowing for all projections to be combined in a single step in the reconstruction, which actually allowed for a much improved reconstruction or quality of the reconstruction of the 3D dataset. And if anyone is interested in finding out more or using this reconstruction algorithm, have a look online or please get in touch and I'd be happy to talk about it. So now that we have a reconstruction algorithm, the next question was having an high resolution experimental setup. We were very lucky that in parallel, at the CSAX beamline at the Swiss light source, they were developing a high spatial resolution laminography setup for tychographic laminography. And you can see in this video that they were able to perform very high spatial resolution non-magnetic laminography of an integrated circuit, demonstrating that essentially the quality of the data that they have access to was exactly what we needed. So we were able to go to the CSACS beamline and take advantage of this new setup to perform a first demonstration of magnetic laminography. And what I want to emphasize here is that actually laminography has a huge advantage for magnetic imaging in that with a single rotation axis, all three components of the magnetization are probed, meaning this is actually a very simple measurement compared to tomography. Now, the sample that we were going to image in this first demonstration was a gadolinium cobalt film. Essentially, we patterned a thin film or a thick film with the focused ion beam, and the film exhibited a varying magnetic anisotropy through the thickness. In order to image the 3D magnetic vector field, we measured such two-dimensional eccentricity projections, as you see in the bottom, for 144 different angles around the rotation axis, and used our reconstruction algorithm to reconstruct the internal configuration with 50 nanometers lateral spatial resolution. So we can see in this reconstruction that we were able to get a very nice understanding of what's happening within our sample. We have a larger in-plane anisotropy at the top, where we have this almost single domain structure, and in the lower anisotropy region at the bottom of the sample, the single domain structure therefore transitions into a double vortex state. A very nice demonstration of the capabilities of magnetic laminography. So this takes us on to our next point on the list, going to the fourth dimension. And one of the challenges here was actually being able to realize the experimental setup in order to be able to essentially perform a pump probe 3D imaging technique. But with the development of magnetic laminography, we realized that we had actually made this job a lot easier for ourselves. Now we could look at flat samples that can be lithographically patterned. And in this way, we patterned a strip line onto our sample, through which we passed an AC current that was frequency and phase matched to the time structure of the X-rays. Now the X-rays have a time structure typically of 500 megahertz, where they consist of 70 picosecond pulses. We then performed magnetic laminography for many different delay times of the AC excitation signal with respect to the time structure of the X-rays. And therefore we're able to obtain four-dimensional magnetic information. And I want to just note quickly that it was not a direct current excitation, but we're actually using the Ørsted field of the strip line in order to excite our magnetic structure. So what we can first of all look at is the vortex state in the bottom of our disk, where vortices are potentially or possibly the most well understood and well-known example of magnetization dynamics that have been studied. And we see actually that we have the vortex processing back and forth over this time period of 2 nanoseconds. And when we plot the position of the vortex with respect to a reference position, we can actually track this very nicely and determine that the domain wall was moving at approximately 200 meters per second, which was a very nice demonstration of tracking a topological object and measuring its dynamics. But of course, it's not just the dynamics of objects that we would be interested in. We also performed Fourier analysis of our four-dimensional data set in order to map the coherent rotation modes of the magnetization. You can see here the red corresponds to regions of high rotation or let's say high magnitude of the modes. And you can see that the magnetization dynamics are indeed closely linked to the 3D magnetic structure, meaning that we can really visualize the magnetization dynamics in 3D. And we were very happy to have this work highlighted on the cover of Nature Nano earlier this year. So now on to the last point in our to-do list, which was the achieving higher spatial resolution of 3D imaging. And what I want to start off by mentioning is that when we talk about going to higher spatial resolutions, if we are not limited by our optics, essentially going to smaller length scales means that we have to improve the signal to noise ratio of our data. Now we can do this in two ways. We can either go to sources with higher coherent flux. We're actually at a very exciting point in time at the moment with synchrotron radiation. So we've got upgrades of the third generation synchrotrons ongoing or in the near future. We've also got the next generation of synchrotrons such as MAX4 in Sweden and Sirius in Brazil online or just coming online at the moment. So this will give us the possibility of up to 3 orders of magnitude more flux in the coming years. In addition, so apart from increasing the flux of our source, we can also just go to stronger signals in order to increase our signal to noise ratio. And this means by going to soft X-rays, where the XMCD signal, as opposed to hard X-rays where it's very weak, here it can be up to 100% of the absorption of our sample. And we've been working on both of these avenues in recent years, but in this talk today, I'm going to mention, we're going to focus more on the soft X-ray 3D imaging, where we have implemented a magnetic laminography setup at the Pollux beamline at the Swiss light source. So when we're talking about soft X-rays, everything's in vacuum and we have relatively small focal lengths, so everything's relatively cramped. But Katerina Witte at the Paul Scherrer Institute did a really great job of implementing the laminography setup for non-magnetic laminography in the chamber, which allowed us to do this first demonstration of soft X-ray magnetic laminography, where we looked at a target skyrmion and were able to reconstruct the 3D configuration with a sub 50 nanometer spatial resolution. Now this is really exciting because it means that with this higher sensitivity and these higher spatial resolutions, we are now have the door open to the study of 3D magnetic textures and 3D magnetic nanostructures. Okay, so now we have ticked off all the points on our to-do list up until now. But as you can imagine, the story is not over yet, and I'm going to take these last 5 minutes of the talk to talk to you about some very recent results that we're quite excited about. Specifically, there is another challenge when it comes to 3D magnetic imaging, and that is of the data. If we remember back to the first demonstration of magnetic imaging that I talked to you about early in the talk, we looked at this 5 micrometer diameter micropillar, and we're able to reconstruct the internal magnetization with 100 nanometer spatial resolution. Now, what this means is that we have hundreds of thousands of spatial resolution elements, each of which contain 3 components of your magnetization vector field. And as you'll remember, we looked at a horizontal slice. We looked at a sub-volume in order to understand what was going on, but it was not possible, it was really challenging to get an overview of what's happening in terms of the internal 3D magnetic configuration. And this is this is one of the remaining challenges of magnetic imaging, and indeed 3D magnetism. How do we analyze and identify complex 3D configurations? And before I go on to this, I want to just mention really quickly that there's a talk tomorrow in the Advances in Magnetic Imaging session from Aurelio Hierro Rodriguez that will also speak a little bit about this challenge. So, our challenge, how do we analyze and identify 3D complex configurations? Well, recently we have implemented a new type of data analysis where we implement calculations of the magnetic vorticity vector, omega. Now I've shown this equation here for those of you who are interested, but essentially what the magnetic vorticity vector is, it's a vector that encodes the topology of our magnetic configuration. Now we can consider a couple of examples of well-known topological structures in order to understand exactly what this means. First of all, with vortices, we know with vortices that the skyrmion number of a vortex is related to the direction of the core of the vortex, so the polarization of the vortex. And we see actually, when we have a vortex, the magnetic vorticity vector is aligned with its core, and it's parallel to the core, corresponding to the skyrmion number density. Now, with anti-vortices, which have an opposite topology and an opposite skyrmion number, the magnetic vorticity vector reverses. And what we can think about then is that this vector omega encapsulates the flux of the skyrmion number density. Now, as you can imagine, this would be particularly useful potentially for looking at topological structures. So we went back to our data set, and by plotting regions of high vorticity, we can actually identify the presence of topological structures within our 3D pillar and actually highlight exactly where they are. Now, in addition to highlighting topological structures, we can also look at the divergence of the magnetic vorticity vector. In this way, we're highlighting regions where the vorticity vector, so the topology of the sample, is abruptly changing, i.e. we're indicating the position of magnetic singularities, and we can see a number of them within the pillar without actually having to look at or look for specific crossover points. Now, in addition to being able to locate and understand structures, the magnetic vorticity vector is also very useful to gain a deeper insight into structures that we are already looking at. And in particular, I want to show you a quick example of a loop that we observed in isosurfaces of the magnetization, where this isosurface corresponds to the magnetization pointing along the x direction. And when we look at this loop, we look at the cross section of the magnetization of this loop, we see that it corresponds to a vortex and an anti-vortex pair. And the diameter of this loop is about 400 nanometers. So this is quite exciting. It was a demonstration of an object that appeared to be stable within the bulk of our pillar. But it wasn't until we looked at the magnetic vorticity vector that we got a deeper insight. Indeed, when we plot the vorticity vector as these arrows in the tube, we see actually that the vorticity is circulating around the tube. And what this means is that it is a magnetic vortex ring. So these magnetic vortex rings were first predicted by Papa Nicolau and Cooper in the 1990s. And they are analogous to hydrodynamic vortex rings, which also exhibit this circulating vorticity of the fluid. But in addition, they're also similar to these vortex rings in a different way. The magnetic vortex rings were predicted to be dynamic structures and not to be stable statically. And the question is why are these structures actually stable? So we can go on to consider quickly the topology of the vortex ring. And in order to do this, we take inspiration from our colleagues who are looking at magnetic Hopfions by plotting pre-images in 3 dimensions, where a pre-image is an isosurface corresponding to a certain direction of the magnetization. Here, for example, the blue loop corresponds to the magnetization pointing in Z, and the red corresponds to the magnetization pointing in a different direction. You see that these 2 loops link a number of times, meaning that they have a non-zero Hopf index and therefore are a Hopfion and have topological stability. When we plot this for our structure, however, we see that the loops corresponding to different directions of the magnetization do not link, meaning that we do not have a Hopfion and we do not have the topological stability. We actually were able to look to gain a deeper insight into what could possibly be the root of the stability by looking for different structures to see whether we could observe more vortex rings within our pillar. And indeed, we were able to observe a number of vortex rings, each with circulating vorticity and each with a Hopf index of 0. And by looking at the structure of these vortex rings, their size and their surroundings, and also performing modeling of bulk textures that were done by Konstantin Metloff, we have determined, or we believe, that it's actually the magnetostatic interaction that is responsible for the stability of these structures, highlighting that the magnetostatics are a very important interaction when it comes to 3D magnetic systems. So just before I conclude, I'd like to thank and acknowledge all of the many people that have been involved in these works that I've talked to you about today, and without whom it would not have been possible to achieve them. The group of Laura Heidemann at the ETH Zurich, people at the Swiss Light Source and the Paul Scherrer Institutes, and my more recent collaborators in the University of Glasgow, the University of Cambridge, Vienna and Donetsk. And to conclude, I've talked to you today about our work on 3D magnetic imaging, developing magnetic tomography, our extension of this to laminography, which allowed us to map the magnetization dynamics in 3D. And most recently, our new, method of analyzing our 3D magnetic datasets, which allowed us to observe magnetic vortex rings. Looking forward, there's a huge amount to be done, and we're really looking forward to making use of these higher spatial resolutions that hopefully we'll achieve with the next generation of synchrotron radiation. We're looking forward to taking advantage of these new methodologies to look at the statics and dynamics of 3D magnetic systems, and of course to join the hunt for these topologically non-trivial 3D structures. Potentially we might be able to observe Hopfion structures in the coming years. So thank you very much again, and I'd be very happy to answer any questions.
So Thank you. That was really a very, very nice talk. Very clear and very wonderful pictures. And I can imagine that there are questions. So if you have one, please write them in the chat, and then we can also, or please write that you have a question in the chat and we can open the microphone for you. So if not, then I start because I wondered how you prepare the target skyrmion that you showed for the laminography result.
So this was actually not prepared by me. It was prepared by my colleague Simone Filizio at the Swiss Light Source. The target skyrmion is a permalloy disc of about 150 nanometers in thickness. And essentially, if it was pure permalloy, we wouldn't expect for the target skyrmion to exist. But the way that the permalloy grows with evaporation, it grows with an canted magnetic anisotropy. So it has slight out of plane anisotropy, and this results in the target skyrmion appearing basically in the structure.
So I wonder if there's a second question coming up. No. Okay, then I ask a second question because
Right.
so when you showed the time resolved measurements, you also did the kind of the Fourier transform. Can you maybe comment a bit more to kind of get the modes, because I didn't really get the color code. What exactly?
Yes, of course. I can go back to that slide. Yep, here we go. So essentially what we're doing here is, so we have 4-dimensional data sets. So we have the 3 spatial dimensions and the, and the time dimension. And what we do is in the time dimension, we are measuring at 500 megahertz. We measure a number of different, let's say, steps for different time delays. And we can, with Fourier analysis, identify the changes in the magnetization that occur at this 500 megahertz frequency. Now, what we do then is we essentially get a number, so we can identify the rotation of the in-plane magnetization, or calculate this using this Fourier analysis, where here the red corresponds to about 180-degree rotation. So you can see in the bottom half of the disk, we see that the red is very much going along the vortex domain walls. And this is because the vortex domain walls are precessing back and forth, which corresponds to 180-degree rotation of the magnetization. So hopefully does that make sense? Okay, great, thank you.
Thanks a lot. I think due to time, we should go onwards. Thanks again for the great talk.
Thank you very much.
Let's move to the next speaker, who is Dédalus Sanz Hernandez. Also, hello.
Hello.
Who was at the University of Cambridge and now moved to CNRS Thales. And he will talk about the chiral control of magnetic spin textures using 3D printed geometries. So please. Perfect, we can see.
Yeah, can you see the screen?
Yes.
Okay, so thanks a lot for the opportunity to present the work here. So, yes, as Claire just commented about the affiliations, I used to work in the group where Claire is, where I did my PhD with Amalia Fernandez Pacheco. And I'm now working at CNRS Thales for a year now in the group of Julie Groyer, doing neuromorphic computing. So the work I'm going to show you today is, it was performed at the ALBA synchrotron with the beamline of Salvador Ferrer. And in this work, we basically study how to control all of these very interesting 3D spin textures that Claire has been showing us. So what we do in this work is we go to a very, very small, much smaller structure in which we employ shape anisotropy to really tune the local magnetization configuration at the nanoscale and exploit shape to generate this type of topological textures at very well controlled places. So I'm very lucky because Claire already did a very nice introduction. So I will basically show you how we use focused electron beam induced deposition here on the left to create a double helix, and exploiting the double helix geometry, we create this type of complex vector fields that I will tell you a bit more in a few minutes. So to start, I give you a small background on dimensionality and topology, so just so that all of the concepts are clear. I start with dimensionality. So dimensionality, we have, in terms of geometry, we can have from zero-dimensional systems, like a point quantum dot, to all the way to 3D, and we are all very familiar with this type of dimensionality. Maybe less familiar to some people is the magnetic dimensionality. So by dimensionality here, I mean the number of degrees of freedom that the vector field is allowed. So for example, we can have a one-dimensional easy axis geometry in which the vector field is strongly favored to point along one given direction. We can have an easy plane in which the vector field is allowed to rotate in a plane. Or for example, in some systems, we can have no anisotropy, so the vector field is allowed to rotate freely. Or we can have, for example, DMI that creates a skyrmion that forces the vector field to rotate in a particular way in 3D, like the skyrmion that Claire was showing us later, before. So this is dimensionality. What about topology? Well, topology are these properties that are conserved under a continuous transformation. And we can have a topology correlated to the geometry, which is the connectivity of the shape. This is a very standard example in which we have a strip and we can connect it into a disk, or we can add a twist and form a Mobius strip, and they cannot be transformed one into another without cutting the strip. And we also have a related magnetic topology, which is related to how the vector field connects. So for example, if we have a disk here at the top with a hole, the magnetic vector field can rotate around the hole and have a continuous link between all of the streamlines. However, if we remove the hole, we change the topology of the geometry, and that leads to a change of the topology of the vector field. And that creates, in this case, a vortex core. Similarly, if we have a one-dimensional system with a one-dimensional shape anisotropy, perpendicular to the plane in this case, when you put two regions of your sample in a different magnetic configuration, here in the center, because the magnetization cannot be reduced to zero, you will force the creation of a domain wall, which is a region of the vector field that points, in this case, transversely to the other spins. So these two entities are said to be topologically induced magnetic textures, and they are protected because of the mathematics of the vector field. What's the interest? Well, these are very interesting entities because of this protection. So they are very stable under external perturbations, and they can be employed as information carriers in the racetrack memory that uses domain walls or skyrmions, for example, to propagate information. They have also been employed to perform logic using current-induced domain wall motion. Or, for example, something that is done very well in the group where I'm currently working is the use of this non-trivial dynamics of the vortex core, this topological entity, to perform neuromorphic computing. Also, you can not only they can not only be the information carrier, but they can also act when they are in an extended geometry as information channels. So, for example, here they employ a one-dimensional domain wall to propagate spin waves in a very efficient way. So, why are we interested in looking at the manipulation of these objects through shape? Well, shape allows a very complex topological geometries. So basically, you can change the topology of your geometry in ways in which the a two-dimensional samples doesn't allow you to do. And also, you have access to a much more sophisticated control of shape anisotropy when you go into 3D. There are many ways to induce 3D magnetic textures using, for example, also DMI or material properties. But in this work, because we have access to very good lithography techniques, we will focus only on using shape. So in particular, what we're gonna use is we're gonna combine two shapes, two basic shapes. One sphere in which the magnetization is free to rotate. So we do a three-dimensional freedom, but we also use nano wires, which are one-dimensional magnetic anisotropy. Depending on the diameter of your nanowire, this anisotropy can be very strong. But okay, so we will control the anisotropy of the vector field, but we will also control the topology. And how we will do this is by having two nanowires and inducing a small overlap here in the center that you see here. So if this overlap is small enough to have the right coupling, then you will induce the creation of a domain wall like the one I described before. And this domain wall can have an associated chirality, which is the direction in which the magnetization rotates as you go from one arm to another. And this chirality can be right-handed or left-handed. I show the two cases here on the right. So with all of these ingredients, what we do is we study the system that I show here on the left. So basically it's a pair of double helices. And critically, what we do is we change the chirality of the helix at the bottom and the helix at the top. So basically, we can not only control the shape anisotropy, but also we add an extra degree of freedom, which is the chirality. And here at the middle region, we induce the interfacing of two spin textures of opposite chirality, which is also going to have a topological consequence, which is that the chirality of a system is a topological constraint as well. And when they match, you will create a topological defect. So you can think of this system as 5 basic interacting geometries, 4 nanowires. We induce an overlap, and then we induce a chirality in order to choose this sense of rotation of the magnetization vector field in each of the double helix structures. And to give a bit of a more magnetic overview, there are 3 interactions taking place in the system. The straight field is favoring the anti-parallel coupling of the arms in the double helix. Also, exchange is forcing is favoring the parallel alignment of the arms, as well as when the straight field wins, it will create this domain wall that I was speaking about earlier. And also we include chirality as a way to choose the sense of rotation. So to have everyone on board, the top here is right-handed and the left, the bottom is left-handed. So as Claire mentioned before, we employ 3D nanofabrication. In particular, we use focused electron beam induced deposition. Here we use a computer via a script or a computer edit design file to control an electron beam, and the electron beam in an electron microscope. And with this, the associated electron cloud, we decompose a gas, in this case is dicobalt octacarbonyl, that leaves a very pure, around 90% cobalt deposit, solid on the substrate, and the carbonyl is extracted by the vacuum pumps in the microscope. So by scanning the beam, applying some corrections, you can basically create any 3D shape that you want. You can have more details here, and as Claire showed before, the group in Cambridge and now in Glasgow, they're very strong at this. So to characterize the system, to look at the magnetic configuration inside, sort of like what Claire was doing, but because this structure is much smaller, we only do 2-dimensional imaging. We go to the ALBA synchrotron at the Mistral beamline, and we perform a soft X-ray microscopy. You can choose the X-ray polarization with a slit placed in the X-ray cone. And basically, by taking two images, you can have a contrast related to the magnetization component along the X direction. Critically, we have tomographic capabilities. We don't take as many images as Claire, so we only take a few. But still, we can have a very good idea of what the magnetization vector field is doing inside the nanostructure. Okay, so when we actually look at the structure, we get a very exciting result, which is that we actually see that the anti-parallel arm configuration is a stable one. So this is rather surprising because, well, we were not sure if this complex magnetic configuration was going to be stable. But when you look at the XMCD image of the structure, you observe this very characteristic positive and negative contrast. Sorry, there was a message. Positive and negative contrast that shows us that at every given height of the nanostructure, all of the magnetization is pointing either towards the viewer or away from the viewer, and this is really related to this anti-parallel arm configuration. And what is very interesting here is that the domain wall that forms is actually not a simple domain wall as I showed you before, but because there is a twist to the system, and one arm is pointing up and the other one is down, there is a helical domain wall formed as in the core, and this helical domain wall is stabilized by the dipolar interaction of the two arms. So we find it very exciting that this structure is stable. And in fact, we also find that you can actually go into a different state when you apply an external magnetic field. This state is shown here, which is the one that is being favored by the exchange interaction. And this state is shown here on the right, which is very similar to what is formed in a very thick nanowire. It's a vortex state in which there is a core and there is a rotation of the external shell of the vector field around this core. Importantly, what we find is that when you apply this magnetic field, you go into this vortex state. However, the chirality of this state is determined by the right-handed or left-handedness of the double helix that is formed geometrically. So we can control with the geometrical chirality the magnetic chirality of the system. So this is very interesting because it allows us to place at very well-defined locations magnetic structures of a given chirality. And in fact, what we can do is actually interface two structures of opposite chirality. And this is what we do here in the bottom. And what happens when you do this is that you actually create a three-dimensional vortex state. And what we do to look at this is we'll perform images at different angles, and we identify the vortex as a change from a circular contrast to a split contrast. And in fact, what happens is that you have gone from a two-dimension, from a left-handed domain wall. What we do here is we untwist the magnetic configuration, and what we see is that we go from a left-handed domain wall to a right-handed domain wall. And to do this, we have to go through a topological constraint that is a nil defect. And this nil defect creates this three-dimensional vortex state. So to conclude, what is very exciting is that there is another solution to this vector field, which is the block point that Claire was talking about. So in simulations, we observe that there is another solution to the discontinuity in magnetic chirality, and this is a block point. So this is very exciting because this technique will allow us to place a domain, a block point at a very, very well controlled location, and maybe studied in a lot more detail with techniques such as what Claire has been showing to really explore the dynamics of a single isolated block point. So with this, I will conclude because I'm running out of time. So I will skip the summary and thank everyone, collaborators in Glasgow, Cambridge, Zaragoza, Berkeley, and Barcelona. And thank you all for your attention.
Yes, exactly. We can have reactions. Thank you very much
No problem.
for the nice talk. It's a really nice combination of how the geometry affects magnetism. I like it. It's very colorful. If there are questions, of course, I'm waiting for the chat. Please. So we do have time for questions. Sorry for. So we have some reactions.
Yeah, I was getting a message at the top, but I was not sure if it was the chat or what was it.
Then maybe I'll ask a question. And what kind of 3D? So you showed the near defect, the Bloch point. Do you think you can also engineer by the geometry other kinds of topological defects?
Yes. So what is very nice about this is that you can induce one-dimensional anisotropies when you put nanowire, for example. So we use only 2 nanowires here. So you can think about using 3, 4, or other systems, or even making, knots with this. So there is still a lot to understand and to imagine. So really, we think that there is a very big place of a very big number of things to play with, only using shape. And we really hope that we can access much more complicated spin textures.
Great. Okay, I do not see another question.
Okay.
Thanks again for your very nice talk. And I think we just move on to the next speaker. And our next speaker, is Thomas Blachowicz from the Silesian University of Technology in Gliwice, Poland. And he will present on the magnetization dynamics in nanofiber networks.
Yes, thank you very much for the introduction. And I am in a virtual state, but I really feel excited. So believe me, it's not a virtual. I hope you can see my screen in the full mode. Yes, please confirm that everything is okay. All right. Okay, fantastic. So my talk was also contributed by my co-workers, by my students, Paweł Stębiński and Jacek Grzybowski, and by Professor Andrea Herman, who is with us today. And at the beginning, I'd like to talk a little bit about inspirations which came from different sources. And so the first inspiration was derived from the material science, because especially in Bielefeld, we prepared nice and very complex structures using electrospinning technology. And in this way, we can observe very complex systems which remind us the structure typical for neurons. And this is why we try to also simulate magnetization dynamics in such structures, in the fibers especially. So we tried to simulate different shapes, different curvatures and orientations. So the first yes, inspiration comes from the material science. Also, the interesting point is when we try to understand magnetization dynamics in at the connections and at the crossing places of different fibers. So we try to simulate something, and we try to observe domain wall transport through such places. This is just a quite narrow topic, but what is really in the background is a so-called neuro-inspired issues. And let me show you two slides of these types where some general information is provided. So looking at the real biological structures, we can observe in real neurons short range and global range propagation of information. In this way, we can identify something like an elementary source of the information, but the another issue is the connections between such elementary biocells. And also we observe in such systems some type of asymmetry. So the information propagates from, let's say, from the left to the right. So we also, I hope, in the future we try to observe similar things in magnetic fibers. And also the last information is that the information processing in such systems is quite complex and is triggered by the series of impulses. Information is coded by this propagating series of impulses rather not by the single events. From that results 7 postulates. It was written by me, by my colleagues. So the elementary unit of information and is a complex spatio-temporal property. The signal processing should be based on the wave-like propagation. A notion of information is also complex, and it is coded in frequency and the phase. And so on and so on. You can read it later, these postulates, but I think that using a simulation, micromagnetic simulation, I will present you today. Preliminary, we are more or less within the first 4 these postulates. So this the last 3 is still a challenge for us, and we will see what will happen. So at the beginning, I will show you something which can be named like a processing unit, a single element, which was simulated by micromagnetic, well-known to everybody simulation using so-called LLG equation, in where we can determine some 4 elementary processes: precession of the magnetization vector, damping, so a change of the direction of the magnetization vector. In any case, we can observe reversal of this vector, and of course, involving some material properties, we can observe some damping. What you can see here is a real fiber, I mean a virtual fiber, of course, and the length of this fiber is 1,570 nanometers. And at the beginning, at the speed of propagation of this domain walls is about 40-50 meters per second. Of course, the speed also can be changed and can be tuned and modified, but our aim of our investigation was to make a system to discover some logic, some elementary logic operation, and we try to do it by using such elementary unit with a given curvature and the cross section. So the question is, what will happen if we made a system more complex, connecting 4 such elementary band fibers? And in this case, we will observe some logic operation. I will show you the result within a few minutes. So by consideration such a simplified setup, which consists of the 2 fibers, 2 band fibers, we assume that here and here there is like an input, and the input is represented by the local circulating field. Here in this figure you can see something which what circulates into the right, here into the left, and the direction of this circulation can be understood like an input state. So into the right, let's say, will be 1, and into the left will be like a 0, like a binary digital 0. At the end of the fibers, we will observe the outputs. So what we expect at the ends, we expect something very static, a state which is very static in time, and something which is oscillating. And also in this way, the output state can be defined like a 0 or 1, yes, so oscillating or non-oscillating state. And we try to simulate such a doubled system, and using permalloy, a lens was provided to you. Cross-section dimension you can see here at 10 times 60 nanometers. The frequency of the field is 500 megahertz. The external field is quite large, is 1 Tesla, magnetic induction. And here you can observe the time evolution of the system at the outputs. So here is a P0, P1, and P3. So here you can see that at the beginning there is nothing interesting. The situation is static because we observe the propagation of these domain walls and into a given direction. And finally, we can observe oscillations. So, using, for example, LL configuration, this LL is related, as we remember, to the inputs. So direction of rotation LL. We observe some characteristic oscillation of the magnetization components. Here, the figure are seen for the P0 output. If we change direction of rotation of one of the input, nothing interesting can happen. So the situations are the same here. So we can conclude that the single output P0 is not so sensitive to provide any logic in the system. So in other words, the system is not enough complex. Also, the same story for the P1, or similar story for the P1 output. Here, a situation is better if we measure or sense this output, because these 2 situations are quite different, and in this way we can observe. We can say that okay, P1 is somehow sensitive to input states and can be applied for any logic. Here there is the whole table of all possibilities for the 4 types of inputs. We can observe some outputs, and we can conclude, yes, the logic is possible, but it is still a little bit limited. So we should try to extend our consideration to more complex system, and I will concentrate now on this 4-level system and show you some truth table. Excuse me, this is for 3 wires still. And I can identify, if here by the light red color, I can, if I identify the inputs, I can look after outputs. So the logic is still limited, but here for the 4-wire system, there are more opportunities. For example, if I use as input S2 and S3 places in the system, here I can observe adequate logic, namely conditional, negation, or projection, well known from the digital technology. Here there is something. If I choose as is 0, S, and 1, I can identify typical NAND or converse non-implication or negation, which is fundamental for the logic efficiencies. Also, using another inputs, I can observe NOR operation, material non-implication, negation of Q system. So this is shortly what was presented, because there is a huge background behind this presentation. This is an issue about simulation. It requires quite strong computing power. I do this simulation using 80 cores machine, and yes, but this gives us some hope that this approach will provide soon some similar inspired logics for future computing based on this new dynamics. So thank you for your attention. I hope it was quite fast, and now maybe I'm waiting for your questions.
Yeah, thank you very much for this talk and also some references.
Yes.
And okay, for questions, please write questions in the chat if you want to give a question, and then you can speak up and ask a question. Maybe I'll start. So I now understand that you have rotating fields that excite your system, and the field strengths seem relatively high. If you were to change the geometry of your wires, would you make it somewhat more favorable?
Yes, I know that it was example of the really with a huge field. I know, but of course I can try with 10 times lower intensities, and it still works. Of course, it still works. So this field, 1 Tesla, was chosen by accident, only to show some new features and some new effects. That's all. Yes, but I know that in real experiments with microwaves, for example, there is the fields are a little bit lower. The interesting point is that it's not so easy in typical micromagnetic. As I said, there is a background issue with micromagnetism and micromagnetic simulators, that it is not so easy to apply the local fields and the local measure points in typical open free micromagnetic simulators. It is not possible. So here we implemented some new functionalities, new features. Yeah.
Okay. The size. So do you expect this propagation to be very sensitive to? So if you were to have like T junctions, would your system lose the functionality?
If I change, excuse me, what? If I change what?
So in principle, the bending radius of your geometry, because you have the half circles.
Yes.
Would it still work if you were to have a T junction with completely straight?
Yes, absolutely, absolutely. I mean, the situation will be quite different. So the bending can tune the propagation and the dynamics. So yes, it's a matter of time, but I should try with a different bending ratio, radius, also in the limit with the typical T shapes. So yes, it will be tested.
Okay, thank you. Are there further questions from the audience?
No questions.
So far, yes. Okay. From our technical host, David, are the fibers like cylindrical wires or squared stripes? And how the cross-section would modify your results?
Absolutely, we'll modify it. So we perform different type of simulation with basically 3 types of cross-sections. So here there is a rectangle, but also with a normal circular, and also with like an oval, a little bit cutted oval. This cross-section a little bit was similar to real technological deposit fiber on the substrate. Absolutely, the results depends on the cross section. Yes. This is
Miriam Jaffa, you wish to ask a question? No, not sure. Have you considered stress in your fibers?
Stress, yes, it is possible also in the simulator, but not yet. But yes, I have such an opportunity to use a stress because it is included in the simulator I used, and I derived these results. Also, I can also include different types of fields, for example, Jawoszyński-Moria interactions of different types. Also temperature. So the results can be tested not only using LLG equation, but also LLB, so-called equation. So we work on that with my coworkers. Yes, so many things.
And just from my side, a follow-up question regarding the fibers. What are the usual diameters? Because I think I just didn't see. Or
you mean real fibers?
Yeah.
Oh, so you mean this picture?
Yes, because they're very long.
Yes, they are very long, and diameter is, you can see the scale here. There is a maybe it's not so clearly visible. 2 microns here, 2 microns, so 2000 nanometers. So real fibers are quite long. Simulated fibers cannot be so long because it requires a huge amount of memory. So it is still. My simulator has 2 terabytes of RAM, but it is not enough.
Right. Okay, that sounds challenging, and good luck on those endeavors. And I think we will thank you very much again for your talk.
Thank you very much.
And we are on time. So for our next speaker, who is he in the session? Yes, okay, yes. Thank you very much. I didn't see. So I'm happy to introduce our next invited speaker, Stuart Parkin. Hello. From the Max Planck Institute of Microstructure Physics in Halle, Germany. And he agreed to give a talk on anti-skyrmions and Bloch-skyrmions in inverse tetragonal Heusler compounds. So all the 3-dimensional structures you've seen so far hopefully help with the understanding. So Stuart,
Okay, can I begin?
Yes, you can begin.
Okay, well, first of all, thank you so much for the invitation to give this talk in this very interesting session. And the talk, I promised to talk about anti-skyrmions and Bloch-skyrmions. So I want to talk about them in the context, a little bit, in the context of how we could use them for, how they could potentially be useful for racetrack memory. So I want to briefly discuss that. Just as a point of view, sorry?
Just I think you're not screen sharing yet, just so that you.
Oh yeah, I'm screen sharing. Oh, sorry. I try again. Sorry.
Okay.
Let's see. I was sharing it originally, then I had to stop. There we are. Thank you for pointing that out.
Okay.
Is it working now?
Now we see it. Yes, thank you.
Oh, so we start again. Thank you very much for this invitation. I'm going to talk a little bit about anti-skirmions and block skirmions in Heusler compounds, and in particular, how they relate to racetrack memory. So I'm currently at the Max Planck Institute for Microstructure Physics, and I just want to briefly, introduce some of the people involved in this work, in particular, Changping, Ranasana, and Andre and Kirill, and some others throughout the talk. And these are some of the people in my group here. And these are some of their names. And also I want to acknowledge a very intense collaboration with Claudia Felser's group in Dresden, who provided the single crystalline materials in which we detected some of these very interesting non-collinear spin textures. And also want to particularly thank Birger Goebel and Ingrid Mertig at the Martin Luther University for their calculations of some of these non-collinear spin textures. First of all, let me just briefly remind you, since this session is about functionalities and potential devices, I wanted to mention, just to remind you, many of you are familiar with this concept of racetrack memory that I proposed a decade ago. And the concept is, of course, that we have magnetic nanowires, which could be on the scale of 20 nanometers in width, in which we create magnetic domains, shown here as red and blue, and the information is encoded in the domain walls between these red and blue regions. And the point of racetrack is that we can move the information around these racetracks using current pulses, and then use reading and writing devices to enable us to see those domains or those domain walls. Concept here is, in principle, we could build a solid state memory with the capacity of a magnetic hard disk drive if we could build these three-dimensional wires, which is incredibly difficult. Nevertheless, in the last few years, we've made enormous progress in racetrack, and in particular, we were one of them. I think we were the first to demonstrate that we could create and move a series of domain walls backwards and forwards using current pulses. And that was originally, that was about 10 years ago, in racetracks shown here on the top left, which were in-plane magnetized. And in in-plane soft magnetic materials like permalloy, the domain walls are very large. Moreover, the domain walls can grow and shrink enormously because they're basically determined not by exchange and anisotropy, but they're determined by exchange and dipole fields, and then the dipole fields are long ranging, and these give rise to large objects. I want to come back to that towards the middle of my talk about anti-skirmions. Anyway, those domain walls in those early days could be moved at about 100 meters per second when we apply current pulses, and the mechanism was spin transfer torque. In other words, the current passing through the material becomes spin polarized, and we could use that spin angular momentum to manipulate the domain walls. And as we demonstrated then a decade ago, this gives you a maximum velocity of about 100 meters per second without burning up the wires. Then we could switch to not in-plane magnetized, but in racetrack 2.0, perpendicularly magnetized domain walls, in which now the domain wall size is a balance between exchange and the anisotropy, the perpendicular magnetic anisotropy. This shrinks the domain walls enormously down to a nanometer, a few nanometers in width from a few tens or hundreds of nanometers. So this is more interesting technologically, and these domain walls are useful technologically. But then again, using spin transfer torque, volume spin transfer torque, then these domain walls again move in the direction of the flow of the spin angular momentum, as you can see in this diagram, again at about 100 meters per second. So the shrinking of the domain wall dimensions did not make much difference to the velocity. Then in the last two stages, if you like, we've evolved to using spin orbit torques, which means that we pass current through a neighboring layer, a heavy metal, typically like platinum or tungsten or alloys, in which we convert charge current to spin current. The spin current flows from that layer. Here would be platinum, this yellow layer shown in the racetrack 3.0 on the left side, and the domain walls then move in the opposite direction to the volume spin transfer torque. And then can now move at a few hundred meters per second, about 3 times faster for the same current density. And then finally, we need to eliminate the long-range dipole fields. And we can do this in something called a synthetic antiferromagnetic racetrack. And this is an idea that I invented 25 years ago, and which has been used in all sensing devices in magnetic disk drives since that time. And the concept is, on the nanoscale, the dipole fields become so large that they cause interactions between layers within a vertical stack, or in this case, from one domain wall to the next one. And we've demonstrated, at least by simulations, that let's say if you do not use this synthetic antiferromagnet, but just use a ferromagnetic layer, as shown here in racetrack 3.0, then neighboring racetracks cause interactions between the domain walls through dipole fields and cause the domain walls not to move reliably. So the racetrack is super important, and that's something that we demonstrated in 2015 in this Nature Nano paper. And now it's been, other groups have followed this lead and have used synthetic antiferromagnetic racetracks, and also with respect to skyrmions and anti-skyrmions, there's a lot of interest there too. Let me just end. So this is, if you like, just to remind you, the synthetic antiferromagnetic racetrack you see on the top left. You can see the structure. The green and blue layers correspond to ultra-thin layers of cobalt and nickel, which give rise to perpendicular magnetic anisotropy. And two of these perpendicularly magnetized heterostructures are coupled through the yellow layer, which is a thin layer of ruthenium, 7 angstroms thick, or in that range of thickness, couples them strongly antiferromagnetically. The orange layer, the platinum layer, is the one that gives rise to two effects. One, it gives rise to this spin Hall effect, conversion of charge to spin current, and the spin currents then created by this spin Hall effect in the platinum layer diffuse into the lowest layer, the green layer, the cobalt layer, and they apply spin torques on this layer and can move the domain walls. But in this synthetic antiferromagnetic racetrack, we discovered that the antiferromagnetic coupling through the ruthenium of the lower and upper cobalt, nickel, cobalt layers gives rise to an additional torque, which we call the giant exchange torque. The size of this torque is reflective of the strength of this antiferromagnetic coupling. And it's so large that it dominates the torque provided through the current provided by the platinum. And this torque then moves these domain walls more efficiently, up to 5 times faster, we found, than the simple ferromagnetic layer. So the cartoon shows you a domain wall. And the point here is that these domain walls, I didn't mention, this platinum layer provides another very interesting aspect, which has been discussed before, which is that it gives rise to a Dzerzhinsky-Meria interface exchange, a vector exchange. And because of the broken symmetry, it's only one interface. This causes the domain walls to be chiral, as shown in this cartoon, and also causes them to be nail-like. So we have nail walls, and the nail chiral symmetry in the lower cobalt-nickel cobalt layer is preserved in the upper cobalt-nickel cobalt layer through the antiferromagnetic coupling through the yellow ruthenium layer. So it's a little bit complicated, but in the end, you have then a structure in which the magnetization in the upper layer is exactly a mirror image of that in the lower layer. So altogether, there's no net moment anywhere in the structure in aggregate. And this means no long-range dipole fields. In these structures, we've seen speeds of up to a few kilometers per second for reasonable current densities. This is a very interesting point. So now in this, this just shows you to do these experiments, we typically use Kerr microscopy, and in the top, you can see the motion of domain walls, a series of them, 20 domain walls, in a simple ferromagnetic layer shown on the top right. A cobalt, nickel cobalt sandwich is 1 nanometer thick, laid on a platinum underlayer, and on top we have a tantalum nitride layer. They move at about 300 meters per second. And this, in the middle, you can see a synthetic antiferromagnetic racetrack. These racetracks are about 2 microns wide. And here the Kerr signal is reduced because it's the moment in the upper cobalt nickel cobalt layer compensate that in the lower cobalt nickel cobalt layer. So there's very little magnetization to be detected. Nevertheless, we can see the domain walls move, and they're moving now, in this case, about 1 kilometer per second. So you can see we have this very interesting interplay of 4 phenomena derived from spin-orbit coupling, the perpendicular magnetic anisotropy itself in the cobalt nickel cobalt sandwich, there is a very large proximity-induced magnetization in the platinum layer, which needs to be taken into account when compensating the moment in the upper racetrack on the lower racetrack. The walls have a chirality imposed by an interface of broken symmetry, and there are spin currents derived from the spin Hall effect. All of these have to work together to move the domain walls as they do. Now I want to switch. So this is the basic concept of racetrack memory, and I think it's super exciting, and we could use it both to create a super dense memory, but also because we can move the domain walls so efficiently, we could imagine a device with a single domain wall, and we could build a single domain wall racetrack which could compete with the fastest memory today, static random access memory. And that's something I believe is super interesting and we're working on. Now I want to switch to, well, can we go beyond chiral domain walls? And of course the answer is we could. And there's been a lot of interest then since the discovery of skermions in the B20 materials in manganese, silicon, and iron germanium in looking for other types of non-collinear spin textures. And in the last 5 years, we've discovered several new non-collinear spin textures. Some of those we've discovered in this family of Heusler compounds, which have been extensively explored over the last 20 years or more by, in particular, Claudia Felser and her group now at the Max Planck in Dresden. And so they provided us with some very nice, beautiful single crystal materials, in particular, this series, manganese to platinum tin, manganese to rhodium tin, and manganese to iridium tin. So what makes a Heusler compound or Heusler is that it consists of 4 interpenetrating FCC lattices, the typically involving 2 lattices of manganese. And the manganese moments you can see in the middle cartoon are shown in blue and red. And these systems are ferrimagnetic. You have 2 distinct manganese atoms or manganese configurations or environments. And these moments are aligned parallel to each other in a plane, but anti-parallel to each other from one plane to the next. So these are ferrimagnetic systems. And it turns out then, if you have heavy atoms like platinum, rhodium, and iridium, these give rise to non-collinear magnetic textures. And this was first shown in this PRL by Ms. Cheriakova, who, and with Jürgen Kubler, they suggested that this material shows a non-collinear spin texture at low temperatures, in which they said, oh, the 2 lattices which are ferrimagnetic, anti-parallel at high temperatures, one of them has its moments rotated, no longer anti-parallel, but at some finite angle to the other lattice. That's what they predicted. A simple non-collinear texture. And this was reflected, for example, in the temperature dependence of the magnetization. And we also showed that these systems show a topological Hall effect, which is shown in here, suggestive of some kind of interesting topological spin textures in the material. So I want to then go to remind you that what is a skermion? You all know this. Typically, one sees either a block or a nail skermion. What are they? These are small circular objects in which the magnetization in a perpendicularly magnetized material breaks up into an array of these objects. In the middle of each object, the magnetization is opposite in sign. And so then you have a circular object with a wall, a domain wall. And this, on the right-hand side, this wall is chiral because the heavy metals, platinum, rhodium, iridium, give rise to strong spin-orbit coupling, and there's an intrinsic Dzyaloshinski-Meria interaction in the bulk of the material. And this gives rise then to a chiral spin texture. And on the right-hand side, you can see it's a nail-like spin texture. And that means that as you go from the outside to the inside along the radius, the magnetization rotates from an up to a down direction and rotates along the radius with the component of the magnetization confined to the radial direction. Whereas on the left-hand side, you can see in a block skermion, then the magnetization rotates from up to down along the radius by rotating along the tangent to the object. So they have 2 distinct types of skermions, both are chiral. because the magnetization can rotate in both cases to the right or to the left as you go from the outside to the inside. These are topological objects in the sense that if you integrate the derivative of the magnetization around these materials, you have a topological charge. Now, more interesting is not more interesting, just as interesting is the antiskirmion shown in the middle. This object is found in materials with particular symmetries, so that the intrinsic bulk Silesian interaction has a different sign for different directions in the plane of the material. And here you can see that the system, it's tetragonal, so it has a fourfold symmetry in the plane of the material. And then along certain directions, you have nail-like walls, and along other directions, you have block-like walls at 45 degrees to the nail-like walls. So as you go around the circumference of this object, the wall changes, both in its form, nail to block, back to nail, but also the chirality changes from right-handed to left-handed, right-handed to left-handed as we rotate around the circumference. So it has a very, very interesting structure. And this was theoretically predicted in certain materials. And then we detected them using Lorentz transmission electron microscopy. And just to remind you, this is a technique where you take a energetic beam of electrons, and you have to pass that beam through a very, very thin lamella of the material, maybe no more than 100 nanometers thick. And then you look at the diffraction or the transmission of those electrons. And what you find is that the electrons are deflected to the left or to the right, depending upon the in-plane component of the magnetization through Lorentz forces. So if you take, and this is so what we've done is, Changping has first of all calculated using micromagnetic simulations the structure of block and nail skirmions and antiskirmions by incorporating different symmetries of the Silesian interaction and for certain magnetizations and exchange. And then we can calculate what we would see in the Lorentz microscope. And this depends on the focal plane where you view the transmitted beam. So it's a little bit complicated. Nevertheless, you can see on the right-hand side that a nail-like skirmion actually is invisible in the transmission electron microscope when you look perpendicular to the object. If you tilt the object, then you can see the nail skirmion. On the left-hand side, you can see the block skirmion, which is what the B20 materials display, is easy to see, and you can then see this simple circular object that shows that the beam is focused, or there's an increased intensity of the transmitted beam in the middle of the skirmion. And in the middle, you see the anti-skirmion is more interesting. You basically see to the top and bottom an increased intensity, that white intensity, and to the left and right, you see a decreased intensity. So you see a fourfold structure reflective of the tetragonal symmetry. And then this is what we found. So this is our work. We discovered this antiskirmion in this manganese platinum tin Heusler compound, although in order to form these crystals, then the group of Claudia Felser, they found that they could only form these crystals if there was a strong deficiency of manganese. So the manganese is only 1.4, it's not 2. And originally, there was some incorporation of palladium. It wasn't fully platinum. It was 90% platinum, 10% palladium, although subsequently in crystals without palladium, we can see the same results. And now we've also seen in manganese 2 rhodium tin, very similar anti-skirmion structures. So if you look at the top left in A, this is what a single anti-skirmion looks like in the Lorentz transmission electron micrograph. So it looks just like what we calculated the Lorentz image should look like. And typically, if you look in C, you'll see there's an array, an hexagonal array of these anti-skirmions. And again, this is commonly observed in the skirmion, for skirmions. And then on the top right, you can see our calculation, micromagnetic simulation of what we expect to see. And then the rest of these micrographs, I'm going to talk about a little more detail. But what we found was that depending upon the out-of-plane magnetic field and the temperature, we can see or stabilize these anti-skirmions, or we cannot. And in the bottom right, you can see we can make a single row of antiskyrmions when we shrink the thickness of the lamella through which we are detecting these objects. And so this is shown here in more detail. You can see here that here in the top, you can see a lamella from the side, and using focus time milling, we make a lamella from a single crystal material whose thickness is varying, in this case, from 200 or just 150 nanometers to 250 nanometers. Not such a big variation, but we can vary the thickness from, let's say, 100 nanometers up to a few microns over a length scale of, let's say, 10 microns. On the left-hand side, you can see a Lorentz micrograph. And what you see now in the regions ABC, which have slightly different thicknesses, you can see that in low field, here in zero field, we don't see the antiskyrmions. We see this helical texture. So if you look in the row of images from A, first we apply a large field, 0.27 Tesla, and we see for A, we see nothing. And in C, you can still see the thicker C, which is thicker, we can still see some antiskyrmions. If you take A, as we reduce the field, you can see from left to right, we start to see antiskyrmions, which exist over a certain field range, and then we start to see these black and white lines, which correspond to a helix. The magnetization is rotating out of the plane, then into the plane in a helical fashion along this direction you can see here. And this direction of the helix is fixed in this system by the underlying crystal lattice. And as we increase the thickness from A to B to C, you can see there are some differences in the field range of which we see these different spin textures. Nevertheless, largely speaking, this phase diagram is insensitive to the thickness. This is summarized in this foil. You can see here, A and B just correspond to looking at the area occupied by the antiskyrmion phase or the antiskyrmion density. But in both cases, what you can see, the vertical axis is the magnetic field from 0 to 0.45 Tesla, and the temperature is varying from 100 to 350 Kelvin. And you can see, we can see these antiskyrmions over a wide range of field and temperature. This is the most important point, irrespective of the thickness. But there are some important thickness dependence I want to come back to. But first I want to compare this with this very beautiful work by Yoshi Takura's group, where they showed, a long time ago now, that in this B20 chiral iron germanium system, they showed that when the thickness of their lamella, through which they're carrying out Lorentz microscopy, they found, as you can see in the top on F, you can see the skyrmion range is in temperature and field is quite extended, but for a 15 nanometer thick lamella. But as they increase the thickness, the skyrmion phase nearly disappears. And you can see this is a big contrast to our own work, where the antiskyrmions are highly stable over the thickness and temperature range. So there's a big difference between antiskyrmions, stable over a wide range of temperature and magnetic fields, as compared to skyrmions, which have a limited stability. This is an important point. So let's say, going back to a racetrack, if we want to use some object to build a racetrack, we need that object to be stable over a very wide range of temperature. And so antiskyrmions look like they would be much more attractive than skyrmions for this purpose. And then Changping has carried out a lot of simulations, and these are simulations in which we only include the Heisenberg exchange and the Delezinski-Maria exchange, reflective of the particular crystal symmetry. And here we compare the B20 manganese silicon iron germanium in the top, and then down below the D2D symmetry, which is the symmetry of this inverse tetragonal Heustler compound. And what you can see, it's very difficult to see in this image, I apologize, but the thickness here goes from thin 1 to 18, which is the numbers of layers used in the simulation. Each layer is 40 nanometers thick, and the left to right is the perpendicular field. And you can see, if you look at the top in the B20 structure, the skyrmion phase is stable only over a limited field and thickness range, whereas the antiskyrmion phase is stable over the complete thickness. It's basically independent of the thickness, neglecting dipole fields. And the reason is because there is in the B20, which is a cubic system, the Dielinski-Maria vector exchange has the same magnitude in all directions. And this causes a twisting of the structure in all directions, and you get basically a spherical object. Whereas in the anti-skyrmion system, it's a tetragonal phase, and the DMI vector reflects that symmetry, and it only has components in the tetragonal plane and not out of the plane. So out of the plane, there is no twisting of the magnetic structure. This explains, we believe, why the untwisted anti-skyrmion tubes can exist over a very wide range of thickness. However, this is a calculation without dipole field. And what we found, interestingly, even for this limited thickness range, here from 40 to 180 nanometers from the Lorentz microscopy, we're looking here not at the anti-skyrmions, we're looking at the helical phase in the black and white stripes, which you can see on the right-hand side. They're oriented in largely in one of two directions. These directions are those directions in which the wall type of the anti-skyrmion is a block wall. This is the lowest energy wall when you take into account dipole fields, dipole energies. And what we found then on the left side, you can see the helical period increases significantly as we change the thickness. Here, the period changes from 100 nanometers to 200 nanometers as we change the thickness of this lamella from 40 to 160 nanometers. So a dramatic increase in the helical period. Now, why is that? First, let's look at a wider thickness range. So here, we're looking at a lamina, the lamella through which we're imaging, varying in thickness from just below 100 nanometers to 1.6 microns. And you can see the size of the helical period is varying from 100 nanometers to 600 nanometers, a huge thickness dependence. In the B20 systems, there are no reports of any dependence of the size of the skyrmion on the thickness of the lamella. Now we want to argue these are real chiral effects. If you look, by the way, this work here is taken using variable temperature magnetic force microscopy, because the TEM, the Lorentz microscopy, is not possible for these very thick layers. And so on the left-hand side, you can see a beautiful magnetic force microscopy image where we're directly imaging the outer plane component of the magnetization. And you can see in the bottom left, the line profile shows you that the magnetization profile varies in a sinusoidal fashion. In other words, it's not a magnetic bubble with chiral walls. They really have a sinusoidal varying texture across the whole film. This is an important point. And then I want to just briefly show you then, this is fantastic images. These are lamella which are 8 microns in width and 60 microns long, where the thickness then is varying from 0.6 microns on the left to 4 microns on the right-hand side. And I think, and these are showing 3 different magnetic force microscopy images where we've changed the magnetic field. So in B, you can see at the top right, you can see this field we applied was at 0 degrees. And then in the bottom here, it's 45, and here it's at 90 degrees. What does that mean? That means we've applied a magnetic field at an angle to the lamella to change the orientations. This is an in-plane field where we varied it from a direction that favors block walls to a direction that favors nail walls. And we can actually rotate the helical structure. So in B, you can see that the helix is pointing vertically, whereas in C, it's rather pointing horizontally. And in D, you can see a mixture of the 2 helical domains, if you like, pointing along the 2 crystallographic directions that favor block walls. From these data, you can visually easily see that on the left, you can see that the lines, the up and down magnetizations are closer together than on the right. And this is because the helical period shown in G is varying from 100 nanometers on the left to more than a micron on the right by a factor of 10, as we vary the thickness from this 0.6 to 4 microns. And we've included here in this summary, if you like, both Lorentz microscopy in the very thin, for very thin lamella. It agrees well with the magnetic force microscopy data. So we can look at how the helical phase varies over this very large wavelength range. And we see this monotonic variation of the helical period. Now, by changing the magnetic field perpendicularly, we can actually then stabilize the antiskyrmions. And these are data, the same lamella, where shown on the top left are the helical phase in zero field. And as we increase the field to 300 millitesla to 420 to 480, you can see the helical phase disappears depending upon the thickness. And we see the antiskyrmions, which in the magnetic force microscope look just like little bubbles. And then you can see eventually we see antiskyrmions in D, and you can see the size. The very small objects are in the thin part of the lamina on the left, and much larger objects on the right in a hexagonal array. And on the right-hand side, you can see that the size or the diameter of these antiskyrmions varies in a very similar way to the period of the helix, increasing monotonically with thickness. And in fact, there's a one-to-one correspondence between the antiskyrmion size and the helical period. So we've seen antiskyrmions up to several microns in size, and we can then visualize them even optically using Kerr microscopy. I wanted just to point out then that in the same material, the same manganese platinum tin material, we can actually see not these antiskyrmions, but we see metastable elliptical block skyrmions can be stabilized in the same material. And these are different from the block skyrmions found in B20 materials. One, out of the plane, they're tubular with no variation, and B, in the plane, the long elliptical axis is oriented along the direction that favors block walls. So these are really interesting objects, and we can continuously transform the antiskyrmions into these block skyrmions. And we see block skyrmions with the long axis oriented along two perpendicular directions, the same directions as the ones where we see the helix. And the reason is these block walls have this lowest energy. By the way, I really didn't discuss why do we see this variation in size, and that is because of the dipole fields. So I didn't include this, I think, but basically we can calculate the energy relating to the magnetic dipole fields, and that is the energy that causes a very interesting variation of the helical period and the antiskyrmion size with the thickness of the lamella. And this means that in thicknesses of lamella suitable for Lorentz TM, the antiskyrmions actually have a much smaller size than you would predict based on what we believe to be the strength of the Dzerzhinsky-Maria exchange. It's mostly the size is dominated by dipole fields. So the dipole fields are really interesting in this regard. We can tune the size in this way. And again, for racetrack, we could imagine devices in which we take advantage of this size tuning to enable us to more easily detect the antiskyrmions when we want to read them or write them, and then we can shrink them when we want to store them. This is something also we're working on. So I just wanted to finally mention that we also see other very interesting structures. One of those is in this a layered compound, platinum manganese gallium, not related to Heusler's. And originally this was thought to be a centrosymmetric material, but we discovered that it actually supports some very interesting neo-skyrmions. And we then found that the structure in the literature, and had been the structure, I think, known for more than 30 years, was incorrect. There is actually a small distortion of the structure, so that it actually has a non-centrosymmetric structure, and it has a layered structure of platinum, gallium, manganese. And this layered structure then supports, it's non-centrosymmetric, and the platinum gives rise to very interesting nail skirmion structure. This is shown here. So these are the images. As I mentioned earlier, nail skirmions cannot be seen by Lorentz. Yeah?
Just, can you please wrap up?
Yes. So nail skirmions. But by tilting, we can see these nail skirmions. And what's most interesting is that just like the anti-skirmions, the size varies continuously as a function of thickness, because again, it's the symmetry of this thing is a layered structure. And so this is, again, a very interesting property. This is a magnetic force microscopy image as we vary the thickness from a range of 0.3 microns to 4 microns. So, and then we find what this one is particularly interesting, because these are metastable nail skirmions, and they're very stable against magnetic fields. So I think this is super interesting in this case too. So since then I want to come to then I want to just briefly mention, well, okay, so our current focus is actually on trying to create thin films in which we can see these anti-skirmions and nail skirmions, because we want to manipulate them. By Lorentz microscopy, we can pass currents through a lamella, and we can see volume spin transfer torques do not move the anti-skirmions. We cannot move the anti-skirmions by current. We need to use some kind of spin-orbit torque, and that's something that we're currently working on by using this thin film deposition system. So I think then I'm going to end my talk here. I tried to just briefly discuss anti-skirmions, block skirmions, nail skirmions in these new systems that we've discovered, that they have unique properties as compared to conventional skirmions that have been most extensively explored in the V20 systems. And I think the future will be when we can create thin films. It's very difficult because we need to form these ordered, atomically ordered compounds with the correct composition. This is something which is not so easy to do in thin films, but 2 years ago we developed a new technique of chemical templating in which we at least demonstrated that we could form binary Heusler compounds, which have the same properties as bulk. To form these ternary compounds is a little bit more challenging, because not only must the composition be correct, but all the elements must be in their correct sites, which is not straightforward. But we believe that we will be able to achieve this soon. And then we're going to use this system here, which we built over the last several years in my laboratory, where we have a 15-meter long vacuum tube connecting multiple deposition systems for sputtering, ion beam sputtering, MBE, pulse laser deposition, also connected to an in situ angle resolve photoemission spectrometer, and other systems for developing these thin films. So I'm going to end my talk there, and thank you very much for your attention.
Well, thank you. Yes, it was really exciting to see that you can kind of tune the sizes so well. And I think we have time for one question. So I suppose there's already one in the chat. And that. Okay, sorry, I was supposed to speak louder.
Oh, okay.
So one question that came up in the chat already, not me, not you, sorry. But how fast would the racetrack need to be, more or less, to compete with today's technology?
Oh, that's a very good question. So it turns out that, let's say, most interestingly, if we could compete with SRAM. SRAM is the fastest memory today, and that basically makes computers work effectively. And the SRAM is the memory closest to the computing, the transistors. So we believe that our kilometer per second means we can actually move these walls on a scale of, let's say, 100 picoseconds. This is, you need to be about 1 nanosecond to be competitive. So we already believe we're super competitive.
Great. Okay, thank you very much again. I think we will move on to the next talk due to time constraints.
Very good. Then I stop sharing.
Thank you.
Very good.
Okay, and we will stay on the topic of skirmions with another invited talk. The speaker is Alexei Sapochnik from the EPFL Lausanne. in Switzerland. And he will talk about manipulating skyrmions by laser light as a route to ultra-fast data storage. So go ahead.
Yes. Can you hear me? Can you hear me well?
Yes, we can hear
Okay.
you. But we
Thank
see
you.
the screen. There's a
Thank
little
you.
bit of, I think if you don't move your microphone, I think it's...
Okay. Yes. Good afternoon, ladies and gentlemen. Thank you for giving me an opportunity to present my work. Thank you for the introduction. In the beginning, I will talk about types of topological magnetic structures and their visualization by Lorentz TM. Afterwards, I will show you the data on photocreation and annihilation of skyrmions in iron germanium. And then I will talk about photocreation of skyrmions in copper selenide, which is insulating in contrast to iron germanium. And at the end of my talk, I will show you magnetic simulation data on photoinduced creation of skyrmions in a racetrack device. Topologically non-trivial magnetic structures have a high stability against external perturbation. This property is connected to the fact that, for example, a skyrmion, shown here on the slide, cannot be smoothly deformed into a homogeneous magnetic configuration. Also, a magnetic structure can be projected onto a sphere by stereographic projection, and a topological magnetic structure is characterized by the topological charge, which is also called a winding number, represented by this integral. And in other words, winding number counts how many times the magnetization vector is wrapped around the sphere upon projecting the magnetic structure. On this slide, I show different topological magnetic structures classified according to their winding number. For example, a Niel skyrmion and block skyrmion have Q equal -1. Anti-skyrmion has Q equal 1. Also under letter F, you can see Meron, which has a winding number of -0.5, because the magnetization changes from in plane to the out of plane, and upon projecting it on the sphere, it will cover just half of the sphere. Also, here you can see skyrmionium, which represents itself two skyrmions, two concentric skyrmions, and the topological charge of a skyrmionium is 0. Also, there are 3D magnetic structures like skyrmion tube or a magnetic bobber, which doesn't penetrate through the whole thickness of the sample, but ends with a block point or magnetic singularity. Having this huge variety of topological magnetic structure, the question arises, how can one experimentally observe them? And several techniques exist, including small angle neutron scattering, Lorentz TM, spin polarized STM, and Mach macroscopy. Each of them has its pros and cons. I would like to talk in more detail about Lorentz TM. On the left-hand side, I show schematics of a transmission electron microscope. At the top, it has electron source and condenser lenses, which prepare the electron beam. Objective lens forms the image, and intermediate and projector lenses magnify the image and project it onto the camera. When electrons traverse a magnetic sample, their trajectories get bent, so the electrons are deviated, and this deviation depends on the local magnetization of the sample. If the objective lens, or to be more precise, objective mini lens, is set to image not the sample plane, but either a plane above or below the sample, white and black contrast will appear at the places where the magnetization changes direction. Also, the Lorentz TM contrast depends on the defocus conditions, as illustrated here for magnetite lamella. Magnetic vortex in the lamella appears white for under focus conditions. It's not visible for in focus and appears black for over focused conditions. When electrons pass through a skyrmion, either block skyrmion or Niel skyrmion, they also experience a Lorentz force, which is indicated by red arrows. And consequently, a block skyrmion will result in appearance of a dark or bright central spot in LTM, as illustrated here for skyrmion lattice in iron germanium. However, for Niel skyrmion in horizontal geometry, there will be no LTM contrast. However, as was already mentioned, if the sample is tilted, then a black-white or white-black contrast will appear in the Lorentz TM image. Many topological magnetic structures were observed by Lorentz TM, including block skyrmions, Niel skyrmions, anti-skyrmions, as was shown in the previous talk by Professor Parkin, and merons. Indeed, Lorentz TM is a very powerful method, providing a high spatial resolution, and it's very often method of choice if one wants to know which type of magnetic structure is present in the sample. Another advantage of the method is connected to transport of intensity equation formalism, which allows for calculating the in-plane magnetization distribution. And here I show the main equation of transport of intensity formalism, where I is the amplitude of the electron beam and phi is the phase. So as you can see, these two quantities are interconnected. And if the derivative is approximated as difference of the images obtained in the overfocus and underfocused conditions, one can restore the phase of the electron beam and from the phase obtain the in-plane magnetization. So in the experiment, it's necessary to take three consecutive images for overfocused, infocus, and underfocus, using identical defocus for both images. And then these three images will allow for TIE reconstruction, and the one can obtain this nice colorful picture which color codes the magnetization direction. Possible applications of skyrmions include racetrack memory, which requires writing and eventually deleting, moving skyrmions and reading them, also skyrmion-based logic, and microwave application, for example, detectors and nano oscillators. And in the rest of my talk, I will concentrate on writing and deleting skyrmions by laser light, which can be beneficial for future racetrack memory applications. To address this question, namely question of photo creation of skyrmions, in our group we use an ultra-fast TM, which is a transmission electron microscope coupled to a femtosecond laser. The femtosecond laser beam is divided into two parts. One part is frequency multiplied and directed onto the cathode to produce photoelectrons, which act as the probe. And the other part of the femtosecond beam is directed on the sample and acts as pump to excite different kinds of dynamics. This slide shows the results on light-induced creation of skyrmions in iron germanium. The experiment starts with the sample in paramagnetic state, and then the sample is zero field cooled so that helices appear in the sample. And then upon applying a magnetic field, the sample state changes into mixed phase, where helical and conical phases coexist. Afterwards, upon shining laser light on the sample gets warmed up and reaches the skyrmion pocket. And afterwards, after cooling down and coming back to the equilibrium state, the skyrmion lattice appears in the sample. The mechanism of skyrmion creation in this case is thermal, and the low energy of 8 × 10⁻⁻15 joule is necessary to write one skyrmion. Also, one can erase skyrmions by laser light depending on the fluence, as shown in this experiment. If the sample in the initial helical state is illuminated by laser light of moderate fluence, a skyrmion lattice is created, and afterwards, upon illuminating with the laser light of a higher fluence exceeding a threshold, the skyrmion lattice is erased. So the sample is in helical phase with some small skyrmion, some handful of skyrmions still remaining in the sample in the corner. This slide shows the data on pump probe, nanosecond pump probe measurements. And the difference with the previous experiment is that for photo creation of skyrmions, the sample needs to be in the mixed phase in the beginning, and then by shining light, skyrmions are photo created. And if the sample is within the skyrmion pocket, so if the parameters are chosen to start with skyrmions already present in the sample, upon illumination, one can excite dynamics of skyrmion lattice and then probe it with photoelectrons. The graphs show intensity of the magnetic contrast, then the skyrmion lattice constant and the orientation of the skyrmion lattice, dependence on the time upon pumping with the neodymium YAG nanosecond laser. As you can see, neither the lattice constant nor the orientation of the lattice changes. However, the drop of the intensity in this case is proportional to the laser fluence used in the experiment. Also, long relaxation time in this experiment are determined by the heat conductivity of the sample. The next study addresses skyrmion creation by light in copper selenide, which is an insulating skyrmion hosting compound. The unit cell of the material is shown on the left-hand side of the slide. There are two kinds of copper atoms, copper 1 and copper 2, having different coordination symmetries. Also, I show the magnetic phase diagram of the bulk sample and corresponding Lorentz TM images. In the bulk sample, the skyrmion pocket extends 5 Kelvin below the Curie temperature. The optical absorption in copper selenide at low photon energies governed by electron transition between the crystal field split 3D copper levels. And these transitions have energies close to 1.5 electron volts. If electrons with a higher photon energy, if photons with a higher energy are used, larger than 2.5 eV, which is the bandgap of the material, then charge transfer from oxygen to copper is activated. And to address the significance of different electronic mechanisms for photocreation of skyrmions, we performed experiment when pumping the copper selenide sample with infrared light of 800 nanometer wavelength and with UV light with a wavelength of 266 nanometers. Please note that absorption for infrared light is much smaller than that for ultraviolet. The magnetic phase diagram of our lamella is different from the bulk sample. The skyrmion pocket extends to lower temperatures in comparison with the bulk copper selenide. And also, upon field cooling, a metastable phase is reached, which is stable down to the lowest available temperature of 5 Kelvin. And this behavior of copper selenide lamella is similar to iron germanium sample shown before. In the beginning of the experiment, the lamella was zero field cooled from above the Curie temperature to 5 Kelvin, and then a magnetic field of 22 millitesla was applied. Afterward, the lamella was pumped by a train of pulses, arriving so with a repetition rate of 300 kilohertz. And before pumping, the sample is in helical state. After pumping with 800 nanometer photons, a skyrmion lattice appears, and the white line shows an approximate boundary of the skyrmion lattice. Also, an interesting fact is that after waiting for 2 minutes without pumping, the skyrmion lattice expands, as you can see in this picture. For the experiment with UV pumping, sample was zero field cooled according to the same protocol. And after pumping, skyrmion lattice appears in the sample as well. However, difference with the case of infrared light is that skyrmion appear in a different part of the sample. Also, after waiting for 2 minutes, as well, the skyrmion lattice expands, so that the area occupied by skyrmions increases. Also, I want to draw your attention to the fact that threshold fluence for obtaining skyrmions with infrared light is 13 microjoule per square centimeter per pulse, which is the absorbed fluence, including already difference in absorption for 2 wavelengths, and that for infrared, for ultraviolet light is 50 microjoule per square centimeter per pulse. To perform control experiment, the sample was zero field cooled to 5 Kelvin, and the magnetic field was applied following the same protocol. However, there was no pumping, and after waiting for 2 minutes without pumping, the sample was still in helical state, so no skyrmions were observed. To summarize the results of this experiment, the skyrmions appear in different parts of the sample when pumped with infrared and UV pulses. Also, the threshold fluence for infrared is 4 times smaller than for UV. And the skyrmion lattice expands after the laser light is off. The next study was inspired by a recent publication in Scientific Reports by Goebel and co-authors, where the authors of the paper suggest creating skyrmionium in a racetrack using Austin switch with circular geometry. SC in this picture stands for semiconductor, and when laser pulse arrives, it enables conductivity and enables charge current to flow from the inner electrode to the outer electrode, and charge current is shown with the white arrows. This configuration of charge current induces spin current via spin Hall effect with a polarization in azimuthal direction shown in cyan arrows. And this configuration of this distribution of spin current can create a skyrmionium. Ultrafast Lorentz TM is an ideal tool for observing this process, since one can combine laser light for exciting skyrmionium and Lorentz transmission electron microscopy for imaging the resulting magnetic structure. Advantage of using a skyrmionium for racetrack memory is that it doesn't have a skyrmion Hall effect, so it's not pushed to the side of a racetrack as it is in the case of skyrmion. And in order to address relevant questions, such as which material parameters are necessary for creating a skyrmionium, or which nanostructure sizes, which nanostructure geometry is favorable, I have performed micromagnetic simulations using MUMAX-3. And the Landau-Lichtenberg equation, in this case, contains 3 terms: effective torque, damping, and spin orbit torque. Also, here you can see the material parameters used for the simulations, which correspond to that of a typical platinum cobalt tantalum multi-layer sample, as well as the simulation world parameters. The plot in the left bottom corner shows the current pulse profile, which is Gaussian with the full width at half maximum around 10 picoseconds. The first question I addressed is the role of the peak writing current. And for a small peak writing current, there is no possibility of creating a skyrmionium, and the color code is as follows. Red dot corresponds to homogeneous magnetization after applying a current pulse, and blue dot corresponds to a skyrmionium. When the peak current is increased, then a skyrmionium can be created for nanostructures with a large outer diameter. And then for peak currents of 2, 4, and 8 times 10 to the 13 amps per square meter, it is easier to create skyrmonium. However, the outer diameter of the nanostructure also needs to be 2.5 times larger than the inner diameter. And I would like to show you some demonstrations, some videos. So here, as you can see, at an intermediate state, a ring of flipped spins appears, which then expand into a skyrmonium. And this is a simulation for a current larger than the threshold current, and also for a large outer diameter. However, if the outer diameter is smaller, then the magnetic structure collapses. And for a lower peak current, also there is no opportunity to create a skyrmonium, so then the magnetic structure eventually relaxes to homogeneous magnetization configuration. The next question is role of the material parameters, namely the DMI constant and saturation magnetization. And in all the simulations, I used the peak current greater than the threshold current. Also for a large outer diameter, one can, in this case, already the color code features homogeneous magnetization for red dot, green dot corresponds to a skyrmion, and blue dot corresponds to a skyrmonium. And for a large outer diameter, it's possible to create either skyrmion or skyrmonium. However, if the outer diameter is decreased, then it is harder to create a magnetic structure. Also, for even smaller outer diameter, the threshold boundary is shifted to higher values of the DMI constant and saturation magnetization. In general, samples with a higher DMI constant and higher magnetization, saturation magnetization are favorable for photocreation of a skyrmonium. Also, anisotropy plays an important role. And at a moderate anisotropy of 700 kilojoule per square meter, the final magnetic configuration is skyrmonium. If the anisotropy is increased, then the skyrmonium collapses to a skyrmion. And for even higher anisotropy, as we will see in a moment, the magnetic structure disappears and the sample ends up in homogeneous magnetic configuration. The other important question is the nanostructure geometry, namely which nanostructure sizes one can use for creating skyrmonium while using a circular Austin switch. And as you can see, it is possible to create a skyrmonium for different sizes of the nanostructures, with the skyrmonium size proportional to the nanostructure size. And this scalable approach is favorable either for initial proof of principle studies, when larger nanostructure can be fabricated easier than small nanostructures, or for applications which require as small nanostructure as possible. In conclusion, I have showed the data on creation and annihilation of skyrmions in iron germanium, governed by thermally induced processes. Then I presented data on photocreation of skyrmions in copper selenide by light of different wavelengths. In this case, electronic processes play an important role. And in the end of my talk, I presented a detailed study of material properties and nanostructure geometries necessary for creating the skyrmonium in a platinum cobalt tantalum sample using scalable circular Austin switch approach. I would like to thank my colleagues from EPFL, also ERC, for funding, and I would like to thank you for your attention.
Thank you very much for your talk and the creation of skirmions. So, as usual, to the audience, if you wish to ask questions, let me know via the chat, and then you can speak up with the microphone. And I do have a question, which is a bit special, I suppose. It's regarding to copper selenide.
Yes.
And some time ago, I also did some experiments on this, and I remember that because the crystal is chiral, you have a very strong dependence when you use circularly polarized light on the absorption. So in one direction you get the absorption is really, really high, and in the other direction it's also high, but not as high. So there's a big asymmetry. Is that ever used in for pumping? Because I assume in the polarization of your laser is rather linear then.
Yes, yeah, the polarization of our laser is linear, but it's possible to use a wave plate to change the polarization, and this is these are future plans. So this is what we still plan to do. Yes, we plan to go for different polarizations, but this study focused mainly on different wavelengths of laser light.
Okay, and then there is a kind of related question from Stuart Parkin regarding the role of the light and whether the role of the light is simply to provide heat. So the local heating would have the same effect if you were to introduce it by different means.
Yes, so for iron germanium, it is simple heating, but the experiment with different wavelengths for copper selenide indicates that electronic processes are important in this case, because if it was just simple heating, then the threshold would be the same for UV and for IR. However, the threshold necessary for the fluence necessary for creating skirmions is different for two different wavelengths. Therefore, this is a strong indication that it's not simple thermal process, but other mechanisms are involved in skirmion creation in this case.
So it's still a follow-up question. So if I can also give microphone, I think you can also unmute Stuart if you
yes,
like to.
Yes, I see the question in the chat. Thank you very much.
If different wavelengths, then that's just could be just simple different absorption, and then different absorption, then of course different temperature. So it doesn't be electronic. And then I had a different question, which would be heating means there must be local heating, local temperature gradients. So you could imagine temperature gradients would cause motion. Do you see any motion?
So thank you for the questions. I will answer them one by one. The first question about heating and different absorption. Yeah, the absorption is different, but I didn't write it on the slide, but I said it that this value already includes the absorption. So this is the absorbed fluence necessary for creating skirmions.
Okay.
And answering your second question, the size of the beam is around 50 micrometers. Some tens of micrometers, and then the scale bar is 1 micrometer, so the beam is much larger than the lamella, so much larger than the imaged area. Therefore, I wouldn't expect any gradient-induced effects here.
Okay.
And then also, beam is very well centered on the lamella. So,
can I just ask one final question? You mentioned 10 to the minus 14 joules to write a skirmion. And I think my recollection may be wrong. In MRAM, the record is a few attojoules to switch a magnetic bit. So it just seems to me that's like 3 or 4 orders of magnitude bigger than the record in MRAM. So why did you say that's so small? It seems like a huge energy to me.
Maybe I have not up-to-date information, but the information which I found for MRAM was of the same order of magnitude. So if you could send me a publication or link, then I would be
sure. Yeah. I think it's from King Wang. It was a DARPA funded program a few years ago, and the objective was to 2 attojoules. I think he claimed to have achieved that. Is my recollection. Could be wrong.
Okay, I also won't argue this case.
Very nice. Anyway, very nice talk.
Thank you very much.
Okay. Are there further questions? If not, for the time being. So the next talk, we have a final talk in this session. It's scheduled in a few minutes. But if you have time and if you're amenable, we could also make a group picture now to kind of, if you were unveiling the screen and activating the camera, you can just have a look with everybody. Nice to see you. And then I can try to make a screenshot for clarity. And yeah, and maybe I'll take this because I suppose you're all getting a bit hungry. Oh, I'm getting a bit hungry, even though I look very much forward to Karen's talk. I just want to tell you, we also have an afternoon session, which is a poster session for more discussions. You're very welcome to join. I hope to see some faces. And also tomorrow morning, there's the other session. And I think I also send the speakers have the program, and the other, the rest of the audience also has the program, because we get the daily reminders of the conference. So let me do a screenshot. And then
But is there any real reason not to start now?
No, I mean, that was actually my question to you, whether you would prefer. I mean, typically you wait in the conference, and if other people want to join, but
so maybe I can just share my screen and see if it works.
Yes, exactly, and I introduce you and your talk. So
is it working?
Yes.
For everybody? Do you see it? Also the slide switching?
Yes.
Okay, perfect.
So, and yeah, it's my pleasure to introduce Karen Devasher-Zitte, who gives the final presentation in today's session, which are about magnetic worlds for unconventional computing. Again, sticking to the Skyrmion theme. Thank you.
Thank you very much, Naomi, for the kind introduction. Just to ask you, just see the slides, not some background or so. Okay, then I will just start. So thank you very much for the introduction. So I'm going to talk about magnetic skyrmions for unconventional computing. And thank you also for letting me participate in this wonderful mini-colloquium. So the structure of the talk is that I will very briefly introduce magnetic skyrmions. So we have heard a lot already in the previous talks. And then I will talk about skyrmions for reservoir computing, an idea that George Boryanov and I came up about a few years ago, and yeah, where we have done already a few works on that. And in the second part about skyrmions using eventually for stochastic computing, where there has been a reshuffler device been actually experimentally realized as a prototype device by the group of Matthias Kloy. So let's start. Magnetic skyrmions, we have already heard a lot, just a bit of history. So there were very early on theoretical predictions by Bogdanov and Jablonski. And the first experimental observation was in 2009 in the form of a skyrmion lattice in manganese silicide. And they occur in systems with broken inversion symmetry. And the reason why, from a theoretical side, why they occur in so many different magnetic systems, as we have heard also in the last talks before, is that what you basically need as an ingredient are two types of different interaction scales. So one interaction where you would like to have them all pointing up, so something that favors a ferromagnetic or some ordering type of interaction, and one that would like to have them canted. And therefore you can have them in metals, semiconductors, insulators, bulk and thin films, low temperature, and of course above room temperature. This makes them interesting, and where they now appear in device relevant systems. And as we have also seen in the talk by Stuart, that their size can be engineered, varying from a few nanometers or a few atom sizes even to a few micrometers. They are detectable by various experimental techniques. You can create, manipulate, and destroy them by various means. And yeah, if you ask why they are interesting, well, this is also what we summarized already. So they do occur above room temperature. This mapping of the topology gives them some additional stability, even if it's not infinite. There has been this early work that they react to very low electric currents. From a physics side, it's interesting because they do have this Magnus force, even though that's something that, depending on the application, you would like to get rid of again. So you have the Skyrmyn-Hall effect. And in principle, there's the idea to use Skyrmyn's force control on its applications as they occur in device-relevant systems. So now we have these Skyrmyns, and you can ask the question about Skyrmyn-based devices, and we have heard already quite a lot about them. And what has so far done often is that you took some device that was working and you put there, or where you had the device concept, and you put a Skyrmyn there instead of another type of magnetic texture like a domain wall. And the typical example is the racetrack device, which was suggested by Stuart, and where then the idea was brought up by Albert Ferrer to put Skyrmyns on the track. Sure, this has some advantages, like these Skyrmyns don't touch the edges, but it also has some disadvantages, like the Skyrmyn-Hall effect, where there also might be some solutions on how to get rid of this again. But still, you can ask also from a very different point of view, what is a device that, if you have these particle whirl-like objects, optimally uses the properties of a Skyrmyn? So when you think of it, then a domain wall is basically a one-dimensional object. So you just need to know where the position of the domain wall is. So if you want to build a device based on domain walls, there's the natural idea to choose a one-dimensional device. But if you look at a Skyrmyn, then it's a particle-like thing that can move in two different dimensions. And or you can use its excitations and have kind of a point particle that can breathe or so. And then the natural device dimension would probably be 2D. So now there have been ideas to extend the Skyrmyn racetrack to 2D. So for instance, by Jan Müller, where he has like this dual lane racetrack device, but still it's effectively 1D transport of Skyrmyns, where they could in principle move in two directions. So therefore, we started to look at what could be ideas where we use this two-dimensional nature of Skyrmyns, and we came up with the directions of reservoir computing and stochastic computing, which is what I would like to explain. So reservoir computing, let's start with this one. So reservoir computing is originally something that is coming from the artificial networks. And they have been studied in a version that all these neurons here in the middle were kept fixed. So the weights of the neurons were kept fixed, and they were called a reservoir, and only the output weights have been trained. But by now there's a field in material research where you take up the role of the reservoir by material. And let me just shortcut the story a little bit. So how does it work? Let's say you have some raw data. Then you need to put this raw data, so people saying the word banana or apple, into a language that your system understands, which could be voltage signals, which means you do some pre-processing with these raw data. Then you feed them through your system, which is, in my case, a magnetic reservoir, but it can be anything else. So people have done this with water buckets, actually. And in my case, it's going to be Skyrmyn fabrics. And then the idea is that this system here acts as a reservoir, which does some nonlinear signal processing in the sense that it projects the signal into a high dimensional space. So, and in this high dimensional space, so now my drawing, this high dimensional space is just 3 dimensions because I cannot plot further. Then in this high dimensional space, I can draw a line and everything, a plane, and everything above are banana and everything below are apples. So I can do data regression by linear, data separation by linear regression. And therefore I have, mapped a complex problem, so differentiating what people have said, into something that is linearly solvable. So that's the goal of reservoir computing. You start off with a complex problem, and you map it to something that's linear solvable. And now the question is, what can you actually put here? And there was an early work by Maas et al. Where they said you can put any nonlinear complex system with short-term memory. So our suggestion a couple of years ago, and by our, I mean George Boryanov, who at that time worked for Intel and now is retired, we suggested to use skyrmion fabrics as a reservoir. And here the idea is to have a complex magnetic pattern and then to apply contacts to this magnetic pattern. And there you can feed in different voltage signals. And then you can also read out the voltage signals. So, and the idea behind it is a bit like this. So you have like a river filled with rocks and stones, and the water is flowing through this river. And whenever the current is strong enough, it might move one of these rocks. So it might move one of these rocks a little bit, and then the water will find a new path, meaning the path still of its lowest resistance. So we are looking at effects where the current adjusts to the magnetic texture. So for instance, AMR effects, so anisotropic magnetoresistance effects, these ones are the ones that we actually model. So here you have our magnetic textures. You are here with Bloch or with Neal type DMI. We have the two contacts. Now we apply a voltage. And if we have some AMR present in the sample, then this is how the current flow would evolve through the magnetic texture. And you can see that where the skyrmions are, for instance, they are stronger or weaker. So there will be a certain current pattern which corresponds to the magnetic texture. So what are the requirements for the reservoir? So one thing is that whenever we initiate the reservoir again, then it should relax back to the same state. So when we turn off the voltage, it should converge back to the initial state. So the skyrmions should not displace significantly for the reservoir to work properly. And now in experiments, of course, there's one idea to move skyrmions, but here we want to keep them fixed. So the way we model it is we model it through grains. So we keep the skyrmions on their place by grain pinning. And now the voltages that we apply are just on that scale that we do get these wiggling around of these skyrmions, that we use the excitations, but they are not overall moving. So this has been shown that the texture topology does not change significantly either through thermal nor through current-driven excitations. So what do we actually observe now? So we look at the time signal, we apply a voltage, so shown in blue, and we apply two different signals, either a sinus or a square, and then we look at the resistance, so the red signal here. And first thing what one can notice is that the reaction of the skyrmion lattice through a sine versus a square is different. So you get a difference in resistance. But the other thing that you notice is that the resistance difference is rather small. So what we observe is when we now apply a pulse of the sequences, so sine, square, square, sine, and so on, then first of all, after some time, there is a very strong nonlinear response. So the signal rises by a factor of 10. So here it's 0.04, and here's another 0 in between. If we would do a linear reconstruction just of adding these signals, then we would get the yellow curve. So we have a very strong nonlinear response. And the other thing that we observe is that already by eye, we can differentiate 4 different patterns. So if we take sine, sine, then we get a resistance signal based on the sine here that just has this shape. If we have a square, square, then it gets this shape, and so on. So this we wanted to study a bit further, not only by eye. So what we did is we did a time tracing first. So that's one approach to do it. So you measure your signal at certain values. And then you would like to know what is the present pulse, what is the latent pulse, so the pulse before, and what is the past pulse. So what we take as a measurement input are the resistance values at these points. So the resistance values at these points. And what we know is what the past pulse was. So for training, we know that this one was, for instance, here a square. This one was, for instance, your sine, and this one was another square. And then we train these weights accordingly. And then once the system is trained, so it's a simple, very simple network, so it's just a single layer network. Once this is trained, then we can also look at the recognition rate. So how good is the recognition rate of the current pulse as a function of these resistance trace samples? So I can either take only 2 or 3 samples, then the recognition rate is not so good, but once I have a certain number, like 10 or so, then I'm pretty good on recognizing the current, the latent, and the past pulse. So time tracing is something that a lot of system also allows. So we also have with this system another advantage, namely you can also read off in principle the signal spatially. So you don't need time tracing. So in theory, what you would do is kind of putting little MTJs on top and then reading out the magnetic pattern or the resistance. And then as a function of these numbers of them, you can also look at how good the recognition is. So the trick is you take only one single snapshot of your magnetization, and from that you can learn about the past. So you can recognize the present pulse with quite a high recognition quality. You can learn about the latent pulse, and you can still learn about the past pulse. So probably combining these two techniques, so like time tracing as well as just taking a spatial measurement, will enhance also the recognition quality. So there's a version to optimize that. So what I've shown you so far is that these fermions do provide a nonlinear complex system with a short-term memory, and you can do very simple pattern recognition by a single measurement. So what are the potential advantages of a skyrmion reservoir? First of all, it can be rather small. The energy consumption is on the microwatt level, and we do have this very high complexity. So scaling up the degrees of freedom is not that hard. So the outlook is, of course, like finding the optimal settings for the magnetic textures and having more than these two contacts, which requires also different code, and then to capture more information about the fabric's response. So with that, let me switch over to stochastic computing. Stochastic computing is something that you don't want to do always. You want to do it when you care about speed, but not too much about precision. And one example is when you want to use your robot vacuum cleaner at home, then you do care about speed, but not whether it's millimeter precise here. Whether the opposite example, when you go to a dentist, then you care about precision, but you prefer to wait 5 minutes longer. So what is the idea behind stochastic computing? For this, let's just imagine a small game. So let's say you win if the red dice is a 6 and the blue one shows an even number, then you know the probability of winning is 1/6 times 1/2 is 1/12. And now we do the experiment. So in the experiment, you can be lucky that you just had a 6 and also an even number, so overall you won. Once you keep repeating the experiment, then eventually you're not always lucky. And what is behind this is that after a while, this one corresponds to or will converge to this theoretical probability by the law of large number. So with the increasing number of experiments, then we will get here on average to 1 out of 6 happy faces, the same as here, 1 out of 2 on average is a happy face. And the other thing is what we did was this multiplication. So this only works if the two cubes are independent from each other. So let's say I glue them together, then for instance, you might never win. So let's now call this not happy face and sad face, let's call it 0s and 1s. And what we then have are 2 bit strings. And these bit strings are related by putting A and B through an AND gate, you will get the out. So, and what we have done by that is multiplying this 1/6 times 1/2. So this multiplication we have performed by means of an AND gate. And now the law of large numbers also tells you directly when something was good or when the results get better. So the longer these signals are, the better the accuracy is on average. And the other thing that we have learned is that these signals must be decorrelated. So what do you do if these signals are correlated? So let's say I have this bit string. So this represents the number 6 over 8. So 1, 2, 3, 4, 5, 6 ones out of 8 numbers. So it's 6 8s. And I just do the same here. So it's also 6 8s. And I've put this, because it's fully correlated through an AND gate, of course, I also get 6 over 8 out. So what I need to do is I need to reshuffle one of these signals in a way that I keep this p-value, so this probability, the same way. And just in the spaces where the zeros are, I just reshuffle. So you put a mixer here, and then on average, it will still work. And there was the suggestion by Julie Grolier's group, with Daniele Pina being the first author, to use skyrmions as a reshuffler based on thermal noise. And so in a very pictorial way, it looks like this. So you put skyrmions into a mixer, and then they come out at different times. And that's something that has been implemented by the Chloe group. So here's kind of the skyrmion mixer. So what you actually do is you have 2 wires, and I hope you can see it. So you have one wire and another wire, and you inject skyrmions in this wire as well as the upper wire, and then you push them into these chambers. So you have 2 chambers, and the idea is whenever a skyrmion comes here through this blue line, then when it's in the upper channel, you call it a 1. Once it goes through the lower channel, you call it a 0. And this is what decodes your input signal. So you get this blue input signal here. And now once they are in the chamber, they will perform the thermal motion, so rather random motion, meaning that they will exit the wire at a different time. So therefore they will be reshuffled once they come out. And in case really there's a full protection of skyrmions and no skyrmion dies, then at some point they will have to come out. So the p-value on average will be similar to that of the blue one. So here I'm going to show now the movie. So you can see that skyrmions are going through, and whenever a skyrmion is going through the lower one, it switches. When it's going to the upper one, it switches. So that is what writes your input signal. And then they wiggle around in these chambers. And once they come out, this is what writes your output signal. So with this, I'm also at the end of my talk. So I've talked to you about skyrmions for reservoir computing, as well as to build a reshuffler device that could be used for stochastic computing. And with this, I would like to thank my group for all the work and my family for all the support, and you for your attention.
Yeah, thank you very much for this very clear presentation. Are there questions?
Probably everybody's hungry for lunch.
Yes, a bit. I can understand that. So maybe just a very quick question regarding the time series that you showed. What do you think how the sampling would be at least to kind of give a good predictive power to the method? How many?
You mean for the reservoir computing part or for the stochastic computing part?
For the reservoir computing part.
For the reservoir computing part. Maybe I share my screen.
So you had the square pulses and the sinusoidal.
So you see my slides? Okay. Yes. So what we do is we only measure the resistance during one pulse for the time tracing, and then we want to know something about the past. Okay. And so how much you can learn about the past depends now on the time correlations that are in your system. So there is like the time scale on which your system is losing memory. So this you can probably see here. After a while, So once I have the sinus signal, during my sine, I have some sort of oscillation in my resistance. And then once the sinus signal stops, I still have some oscillation. And after a while, of course, it's gone. The same with the square pulse. You can see that even if the square pulse stops, there is still this oscillation. So if I wait this full period where my system has lost all the memory, of course, then it's gone. So, but what you can see is that when picking up two signals next to each other, then still there is a history of that. So, and it's going to be a quite subtle interplay on the history of the timescale of the system and on how much you would like to learn.
So in this case, you had taken 10 points on this one pulse and you learned.
For example, here I took 10, but I can show you again the results. So even if I take 20 resistance pulse, I can sample 20 times. I can sample also 5 times. And if you sample 5 times, then you get still a very good recognition for the present and the latent pulse, but then maybe not for the past pulse.
Okay.
But after a while, it converges, because at some point, it's not going to help you to trace more and more and more, because the history about what has happened even before is gone.
Yeah.
Or it's just very subtle only in the system.
But yeah, it's quite impressive that you can look at 5 times, and that's already gives you so much info. So, okay. Thank you very much. I do not see any other question. So I would say we all head to a very well-deserved lunch. And I hope to see you around at the conference. Thank you very much.
Thank you.
Thank you very much.
Thank you.
Ciao.
Thank you.
See you. Okay. So
Noemi,
hi.
you finished?
Yeah, thank you.
You are welcome. Nice talk, really. Pretty nice seminars.
Yes, I really like the talks. It was a bit disappointing to see that not many questions came up. I don't know if it was similar in other seminars.
Yeah, more or less pretty much the same. Maybe the people, when they have to write, maybe they complain. They don't want to write. Let's see.
Well, I mean, they just have to say, I have a question, and then I will give them the microphone.
Yeah, that is true.
Okay,
Right.
let's try tomorrow.
Okay.
And see you this afternoon.
I need you later. What time is it? 4:30 should be? Or 5?
4:45.
Okay. I will arrange everything. When you arrive, I hope everything will be ready.
Actually, we need only 5 rooms, because I got another email asking, and he says he cannot join. Please send this to this email address.
Who is? Do you know?
His I have the program already.
Or send me this email, and I will remove from the rooms.
Okay, good.
Okay.
Thank you.
Okay. See you in a while.
Ciao.
Ciao.
Food. I'm so hungry.